participants. A very good evening to all the participants. On the day 3 of AICTE ATAL sponsored 6-day online faculty development program on unveiling quantum computing from qubits to quantum algorithms. We would like to inform all the participants that due to official commitment of today's speaker, Dr. K. Srinivasan, Defense Institute of Advanced Technology, Pune, he couldn't come and give the lecture today. So there is a change in the schedule. The first session will be taken by Dr. Arun B. Aloysius from IIT Guwahati, who took the first session and inaugurated the event. And the second session will be taken by Quantum Machine Learning, Bridging Quantum Computing and AI by Dr. Ramagowda Dinesh, Samsung, Bangalore. So there is a change. And I would like to introduce Dr. Arun again for those who missed the first session. Dr. Arun B. Aloysius is highly accomplished and dynamic researcher in the field of quantum computing and communications. He earned his BE degree in Electronics and Communication Engineering from Anna University, Chennai, followed by an MTech degree in Electronics and Communication Engineering from NIT Calicut. He completed his PhD in Electrical Engineering from IIT Madras, and he did his postdoctoral research at Duke University, where he contributed to the cutting edge and advancement in quantum research. He also collaborated with Zandu Quantum Technologies as an independent contractor, gaining valuable industrial experience. Currently, he works with IIT Guwahati as an assistant professor, where he continues to inspire students and peers with his innovative work. Already, he took the first session on Introduction to Quantum Computing, and on today, he will be talking about quantum reinforcement learning. I welcome you, sir.
Thank you. Thank you. Oh, okay.
Sir, you can share your screen.
Okay. Okay. Yeah, you can see my screen, right?
Yes, sir. Your screen is visible.
Yeah. Thank you. Yeah, I welcome everyone for my second talk. So hope you have enjoyed the first talk, and hope you will enjoy this talk too.
Yes,
and so this talk will be based on 3 papers. Like the first one is this one. This is the main paper. Like so, quantum multi-arm bandits, which is by Van et al. And followed up references from this quantum amplitude amplification and estimation, and this quantum speed up based on Monte Carlo method. Yeah, so these are the main references for today's talk. Yeah. So with this, I will start giving the talk. And so today, the objective of the talk is to answer these 2 questions. Like, so how can we make quantum information useful by developing some algorithms, some basic algorithms? And second question we try to answer is, so how this the quantum algorithms can be made useful in terms of reinforcement learning. Okay, so I will explain what reinforcement learning is. We will start with what reinforcement learning, and so these are my collaborators in this particular research. Like, so Dr. Argadeep Roy is an assistant professor in Mehta Family School of Data Science at IIT Guwahati. And Bapan Kaudam is a MTech final year student. He MTech in signal processing and machine learning. And Srivatsa is a BTech final year student in EC. With their support, we started learning this particular problem on quantum reinforcement. Okay. Yeah. To start with, now let us think how we learn. Like first of all, like so what do we do for learning? So there are various ways of learning. Okay. And we know everything, like so, and all these machine learning models are developed based on how we learn in the real life. So first thing is, someone might have learned, and they might be teaching us, and we will learn from them like directly. And that's a different type of machine learning, which we are not going to talk about in this talk. Probably the next talk they will focus on that particular topic, how we learn from others' experience and so on. And today's talk is how we start learning by ourselves. Say for example, cycling. So no one is teaching us cycling. Like what we do when we learn cycling, we take the cycle and we just start riding. And when we lose our balance, we adjust ourselves based on the outcome. So what we do is we do some action, and then the environment changes. So we take the cycle and we start pedaling it, and the cycle which is an environment which leans towards some direction, some orientation, so some direction. And now, depending on this environment, we will get some reward. Like so, maybe the cycle may be moving without making any disturbance, or it may fall down. Like so, it's either a reward or like it can be modeled as a reward. Okay, and based on the environmental changes, like if the cycle is leaning on one side, we will change our action according to the environment. And we may change the handle slightly towards the opposite direction to make sure that the cycle will not fall down. And this we learn continuously, and our muscles and our muscles will get trained to this particular action reward setup. We do the action and get the reward, like whether the cycle is moving forward or falling down, and we get the reward, and then we change the action based on the reward and environment, right? And thus we learn the cycle. And this is the whole principle of reinforcement learning. So we learn it by ourselves. Okay. And now let us talk about a simple version of reinforcement learning problem, which is called as multi-arm bandit problem. Okay. Now let us assume you have three chances to take. So in case of cycling, you may change the handle towards left, you may change the handle towards right, and you may go straight. Or in some other sense, you will be asked to choose one of three options. The first option may, so depending on the options, you may get some reward, you may get some money. Say you may get some money. So you'll be given some, you will be asked to pick one of these three, like maybe a 100 rupees note, a 500 rupees note, and a 10 rupees note. You'll be asked to pick one among these. And immediately we will, so if we know the amount, we directly pick the one which is of highest cost, highest price, or highest reward, right? So we always try to maximize the reward. But the problem is we don't know what is there, what is hidden there. We will be asked to take one of these three notes, but we don't know what reward we will get out of these rewards. So what we will do then what we do is like just try the options one by one. So you choose the first option. So you may get a reward of 1. And then, yeah, you will get a reward of 1, and you can stay. There are 2 options. So since you don't know, you know nothing about the arm, you are trying something new. We call this step as exploration. Okay, we try to explore the arm. And once we explore the arm, we know the reward. We know some information about the reward. And now you know the reward. And then there are 2 options. You can either exploit the arm, you know the reward. So you can try to use the arm again and again and gain this reward 1. Or you have other options too. You don't know about arm 2 and arm 3. So you may have to learn about the other options too. So what a rational person will do is he will try and go and try the second arm. So arm 2. So arm 2 may give you a different reward 5. Now you have 2 arms to choose, arm 1 and arm 2. In these 2 arms, reward 5, it's guaranteed. You will get a reward of 5. Say, think about rupees. You will get 5 rupees, and which is higher than the reward that you get in arm 1. So if you want to exploit further, you won't go for arm 1. You will say yourself in arm 2. Okay, but still there is one more arm which is not explored. You don't know what is hidden there in the arm 3. So what you can do is further you go to the next arm and you learn the reward. You learn what is the reward. So you to choose the action as arm 3, and then based on the environment, it may give a reward of 10. And now you know well about all these rewards. Okay, now when the reward is deterministic, you know clearly that this is the better, this arm is better. So you always choose arm 3. So after that, you know clearly, okay, arm 3 has the highest reward. So you pick arm 3 always. Okay, but this looks simple. Like, so you have an exploration, you explore each arm one by one. And then once you understand that this arm has the highest reward, you exploit it. You do that, you use that reward again and again. You take that arm again and again for all the other steps. Okay? And this is the simplest reinforcement learning. This is the simplest multi-arm bandit problem. And then the problem that we face is, what if the reward is random? So now if you pick, say, arm 1, your reward maybe say consider binary reward, like your reward maybe either 0 or 1 with a different probability. Say arm 1 has a reward of 0 with the probability 0.3 and 1 of probability 0.7, and arm 2 has 0 with probability 0.7, and arm 3 has probability 1 with the probability 0.3, and arm 3 has a reward of 0 and 1 with equal probabilities. Now, how will you choose it? Like, how will you learn the arm? Like, the problem is you don't know this reward probabilities. You don't know this R at all. Like, once you choose, you try the arm and you get a reward, and the reward you get will based on this the probability distribution. So you have to learn something from the arm, like, and now you have to learn the whole probability distribution. How will you learn the probability distribution? That is a biggest question that will be kept in front of us. Like, you can't do it on a single trial. The first trial may give you so for example, if you choose the arm 1, the first trial may give you a reward of 1, and second trial may give you a reward of 0. And after that, maybe 100 trials continuously may give you a reward of 0, though it is of less probability, but you may get it, right? So you don't know which arm is an optimal arm with 1 or 2 trials. So you have to try again and again. As you try further, what happens? So when you try it, say for example, you try to estimate the arm 1 for some time. Say you choose arm 1 for some time. Say you'd say 100 times. So x1, x2 up to x100. And what you can do is you can try to take the average of these rewards. So sorry, by 100. So you can try to take the average of these rewards. And what happens is this average converges towards expected mean reward of this. Okay. So now, in some sense, if you try it again and again for a long number of time, the accuracy improves. So with a higher chance, we can understand. We may not understand the probability distribution, but we can understand how this mean changes. And based on mean, you know how this P is for this 0 and 1. So you have to try each arm so many times. But then what is that so many? What is that n? How many times you have to try? That is the next problem that will be in front of us. Okay. So you have to try. But now, so that is the second problem. And again, so think about this reward. Like, so now you have a reward of 5 and 12 and with the different probabilities, 8 and 14 with different probabilities, 5 and 15 with the different probabilities. Again, so in this case, you can just decide with the probability of 1. You can choose the R which maximizes the this probability, this p value, right? Because your reward is 1, you can simply choose the arm. So if you learn the reward statistics, you can always choose this arm, like, every time, because that has the highest probability of getting one reward, like largest reward. But in this scenario, you may not get that kind of benefit. Like, so you will have various different types of rewards, and now you need to quantize it. So somehow you have to quantize it, and that quantization is done by expected reward. So you take the expected value. Expected value is nothing but in a probabilistic version of mean. Yeah, I hope everyone knows it. How to compute the expected value. And now, for example, in this scenario, if you want to compute the expected value of reward for this sum, it is 5 times 0.3 plus 12 times 0.7, which means 70% of times you will get 12 reward of 12, and 30% of times you will get reward of 5. So what will be the average? Average will be something like this. So this, if you compute, it will be something like, can someone compute it and tell me, like, so this number, like, similarly, you can compute this expected reward and this expected reward. So this is 9.9. This is, I think this should be 10 here for the sum 3. And this should be 9.8 something. Okay. So now, if the problem is, if you know the expected reward, now you can see this, like they are almost close, but the arm 3 has a highest expected reward. So which means if you choose arm 3, there is a highest chance that you will get a better reward, like the average reward. So if you try arm 3 say 1,000 times, you will get the reward that you get by arm 3 will be higher compared to arm 1 and arm 2. So we can choose arm 3. But again, the problem is we don't know this expected reward. So that this term we do not know yet. So we have to somehow calculate it. But again, calculating that, if for example, if you compute say 10 times, and if you take x1, x2 to, or say r1, r2 to r10, if you compute 10 rewards and divide it by 10, the expected value of this will be something, the mean of this will be some number, say some a, let us keep it as a. But then the difference between this a and the expected value of r for the single arm, this difference will be can vary between, so the magnitude of this difference can change up to your sigma square, right? So the chances is like there's a term variance which try to represent this difference. Okay, so it can vary. It need not be accurate, and this variance decreases as you increase the number of trials on it. So now the problem is we should find a optimal strategy, optimal number of times you have to try a single arm. You can't always try arm 1 every time. So you have to go for arm 2, arm 3, and so on. Okay. So for that purpose, one of the simplest algorithm for RL algorithm is called as upper confidence bound. So what they do is first they explore every arm, say some n number of times, say 100 number of times. They explore all these every arm 1, arm 2, and arm 3. Say each arm can be, so let us say ni number of times. So first n1 number of times they try arm 1, n2 number of times they try arm 2, and n3 number of times they try arm 3. And total will be n1 plus n2 plus n3. Okay. And now you have to you have to decide which is maximum. So what we do is we call something called as upper confidence bound, and we use this parameter, this upper confidence bounds, to choose which one is maximum. And this upper confidence bound is chosen as mean plus some term which is a function of n and ni. Okay, so this term is actually dependent on this variance sigma square. So this takes care of that variance sigma square. When that arm is tried only for a less number of times compared with n, then this alpha will be very huge, so that mean plus that alpha will be very high, so that you can pick that arm, pick that particular arm again and again, like so that your accuracy for that arm increases. So that is the idea of UCB. Okay, so is that clear? Like, so is that clear so far? Like, okay. So if there are no questions, then I will move forward. And one thing is like, what happens? So what is the bound like? So when you compute the mean, like, so now my mean should be as close as the actual mean. So I wanted how many times I have to try to make it closer towards the actual mean. That one simple bound is given by Chebyshev inequality. And that is this inequality, where mu bar is my mean that is calculated based on samples. You repeat it 100 times. 100 times you explore the same arm, and you take the average of the reward that you get it. So first time you may get 10, and second time you get 5, and third time you may get 4, and then you add them and divide it by 3 in this case, and you get a statistical mean, that is mu bar. And this mu is actual mean that is calculated by the probability. This is like, in this case, it is 0.3 times 0 plus 0.7 times 1. This is nothing but expected value of r that we calculated earlier. Okay. And now we wanted this to as close as this mu bar. So the probability of this getting deviated with the value epsilon is upper bounded by this value, sigma square by ni times, epsilon square by ni times epsilon square. And now if I wanted, where ni is the number of times you use that arm, you work on that arm, you play that arm. Okay. And now the problem here is, now if I want to remove this, getting this accuracy better, if I want to want this mu bar minus mu to sufficiently accurate, I wanted this epsilon square to be removed from this term. It should be, so for arbitrary epsilon, it can become less than some constant. Okay. So now to get that accuracy, I have to repeat the NA should be a function of 1 by epsilon square. Only then this epsilon square gets cancelled. So I want to repeat 1 by epsilon, some order of 1 by epsilon square to get an accuracy of epsilon. By defining accuracy of epsilon, meaning this one. Okay. So I have to run it a large number of times. So in say capital N number of times. Now this is the classical scenario. Okay. So classical scenario, we have to run this many number of times. Now we can think about the quantum scenario, how we can improve this further. And there is a class that in which you can improve this order of 1 by epsilon square to 1 by epsilon, which is much faster, which is roughly square root times faster than this particular classical algorithm. The convergence will be faster. Okay. So for that, we have to move on to the quantum reinforcement learning. Okay. So is there any questions on reinforcement learning? So you have an environment. So you put an action on the environment and get the reward. And based on the reward and the environment, you adapt your action. You change it again and again, and you learn it. You learn the environment. That is the whole idea of this reinforcement learning. Is that clear? Do you have any questions? Okay. So yeah, now we will move on to the quantum version of this. Like with this background on classical reinforcement learning, like we will move on to the quantum version. So just to recall what we have learned in quantum bits, now every qubits can be represented by alpha times 0 plus beta times 1. Like, so all the qubits can be represented in this form, or it can be represented in a vector form where alpha and beta, such that magnitude of alpha square plus magnitude of beta square equal to 1, and alpha and beta belongs to complex numbers. This is how we represent the quantum bit, the state of a quantum bit. And then the operations under a controlled environment, they are all possible unitary operators, u times some psi. That is the controlled operations in a controlled environment. And then suppose if you want to do a measurement, then we model it by projectors, like set of all projectors m1 to m3 mn. So where this many number of separations we make. So that is a set of all devices. And then in case of multiple qubits, you represent it in terms of tensor product. So this will be equal to 0, 0. These are some standard basic things that we have seen earlier. Just to recall that I have mentioned this here. Okay. And now we come into the basic quantum algorithm. So one of the earliest quantum algorithm, I hope you know about this particular algorithm. Most of you who come to quantum algorithm, they know what a Groover search is. And what is Groover search? So Groover search is something like, so you are given a set of students roll numbers, and their ranks will be there. And now you are supposed to find a student with a particular rank, or you have to find a student with a rank higher than a specific number. So in an unorganized data, you are supposed to find a specific data set. That is what the idea of Groover search. And it can increase the complexity from n number of trials to root n number of trials, and the accuracy with some probability, with high probability. Okay. So we can make it faster. That's the whole idea. Like instead of n iterations, you can get the result in root n iterations. That is what the idea of Groover search. And how this Groover search works, that's what we are going to see here. And the generalization of Groover search is called this quantum amplitude amplification. I am going to skip Groover search and just discuss amplitude amplification, because in this RL algorithm, we use this amplitude amplification. Okay. And now how will you start with? So in Groover search, if you have come across, you will start with some state, that is 1 by root n summation over I is from 1 to n, and I. So we do some superposition of all states. So you take 0, for example, 3-qubit brewer search. The first thing is you take this particular state, 0, 1, 0 plus 0, 1, 1 plus 1, 0, 0 plus 1, 0, 1 plus 1, 1, 0 plus 1, 1, 1, set 1, 1. So you take this set which has superposition of all the elements, and it's a uniform superposition. So you take that set as that input as psi. Okay. Now here in amplitude amplification, the problem is you are given a state, something like this. Okay. And here instead of uniform superposition, you have a scalar, you have a value alpha. And now most of the cases we focus only on when alpha is real number, but it works for alpha imaginary to complex numbers too. Okay. But yeah, so that's the whole idea. So we are given this particular state. And now we have two sets, like we can split up the whole set into two sets. You are given some function f of x, and this f of x divides the whole data set into two. It's a binary function. So it is set with the f of x equal to 0 and set with f of x equal to 1. So it is like saying for this particular set, they say, for example, the roll number, say student's roll number and rank. You can make an analogy to student roll number and rank. So I will try to explain all these things with a 3-qubit state. So if you think a student's roll number with the 000 maybe a rank of 2, and 001 maybe rank of 1, and 010 maybe rank of 4, and 011 maybe rank of 3, and 100 maybe rank of 7, and 101 have a rank of 6, and 110 maybe rank of 1 again. 111 can be a rank of say 5. That's the mission. Okay. So suppose this is the ranking criteria. Now suppose you wanted to find a student with rank 1. Now you have to, in classical sense, you have to search through all the data and you have to find it. But in quantum sense, what you can do is you construct a state. In Groover search thing, it is a uniform superposition. But in other general amplitude amplification, you construct some phi, which is a superposition of all this, and it contains alpha. Alpha need not be equal. Like alpha is maybe different. Okay, but when I explain, I will focus on Groover search kind of. So you construct a psi like this, and then what you do is you divide something called psi naught, which is a different state, which captures all these f of I for which the rank is not 1. Like, so we can take the psi 0 as 000 plus 00010. I can't include 001 because rank is 1 plus 011 plus 100 plus 101 plus 111. I can't include 110 also. And again, scale this with some term to make it uniform, make it a valid quantum state. So you have a psi 0 with norm 1. So in this case, it will be 1 by root 6. This factor is just to normalize it. So you put up all these basis, like classical basis states, in one particular quantum state, psi naught. So psi naught is superposition of these classical states for which f of I is 0. Okay. And psi 1 is the superposition of classical state for which the f of I is 1. So in this case, my phi 1 will be like 1 by root 2 times 001 plus 110. Now we are not doing it. The system will this kind of a model. Okay, this is happening inside the system. We are not going to do this ourselves. Like this is just we are trying to study this. Now this is the region of interest. This psi 1 is the region of interest for us. Okay. Now some algorithm will give you this superposition, and I have to find this some elements of psi 1. So what we do is like we can write this psi as some alpha a times psi 0 plus b times psi 1. We pick it in such a way that psi is in this form. Okay. So and a and b are some scaling factors. And normally in quantum amplitude amplification, what we do is, since we are now, if you do measurement on standard basis, the probability of getting something on psi 0 will be magnitude of a square, and probability of getting something on this psi 1 will be magnitude of b square. Something in this region will be magnitude of a square, and something in this region will be magnitude of b square. And our goal will be to do some operation in this psi so that you push this b higher. If b is increased and then you do a measurement, then the chance of getting this result, the result that you search for, is higher. That is this magnitude of B square increase. If you increase B, if you increase magnitude of B, magnitude of B square increases. So our goal is to increase this particular value, this magnitude of this B. And that is why we call this as amplitude amplification. You amplify that particular term. Okay. So far so good, right? And so how we do is like, so what we do is, I have to erase this. I have to erase this to show you this picture. So this picture, you can keep it in your mind. So this is how we do it. And so we have two states. So we can now look the whole thing in two-dimensional picture. So in one part, it is phi 0. This is set of all classical states which we don't need. And psi 1, it is set of all classical states which we wanted. And psi is the state that we prepared somehow. Okay, and either the superposition in Gruer's case. Okay, and we have it, and somehow we have to push this psi to psi 1. So that is the goal. That is the idea of amplitude amplification. This vector, you have to push it towards this point. Okay, so the first thing we do is we flip it with respect to phi naught. So you apply u phi naught. So you flip it with respect to phi naught. Okay, and so the second step is you flip it with respect to phi itself. Okay, so there are two steps. The first step is you flip with respect to phi naught. That is, so you take this vector and take a mirror image of this vector with respect to phi naught. That is the first step. And second step is you take this vector and take a mirror image with respect to this psi. Okay, so that is the second thing. So this one is the mirror image of the earlier vector with respect to psi. Okay, which means now the psi, the original psi, now I have pushed it towards psi 1 to some angle, right? So by applying u phi naught and u phi, just applying u phi naught and u phi. So I call the first unitary matrix that rotates with respect to u phi naught as u phi naught, and the other one with respect to phi as u phi. Okay, so there are two flips. With these two flips, we capture the entire Gruer search. Okay, and so the next step is you repeat this. Okay, you do the repetition again. You flip the vector like so. This will be nice if I show this way. So you have this. So here we have the first flip and the second flip, and then you flip the vector with respect to this red line, and you get it here. And again you flip it now. Oh, sorry. So this is you flip the vector with respect to this psi naught. You get it here, and now again you flip it with respect to this red line. So you get it push towards the psi 1. So it nicely pushes towards the y-axis or the psi 1 which we wanted. Like, okay, and that is the whole idea. And we have to repeat these two steps for n times. And remember, if you make it more than n times, then again it will go towards the other side. Like, so if I run it again and again, then there's a chance that if I run it again, then it will come here and it may go somewhere here. Again, the amplitude of psi 1 gets reduced further. So I don't want to push it for a long time. So I have to push it only for some number of times. Okay, and that numbers you can, if someone try to understand Gruer's algorithm, you can read it through the papers. Like, so papers are the standard text. They will there's a standard way to find out what that number is. Okay, and if you see that number will be proportional to this B, the value of B. So that is magnitude of B. Okay, so here it should be magnitude of B. That is proportional to this magnitude of B. Okay, and that is a key catch. Like, so in classical sense, this will be similar to B square. In quantum sense, it is becoming B. Okay, and this is the idea of quantum amplitude amplification. And once it becomes higher and higher, you do the measurement, you make the measurement, so you get the chance of getting something from phi 1 will be higher. Okay, so that is the whole idea of Gruer's amplification, the quantum amplitude amplification, and that is the essence of Gruer's search algorithm. Okay, and before stopping for questions, I will discuss some more points about this amplitude amplification. Now there are two challenges we are facing. So this amplitude amplification is built upon only two reflections. So U psi naught and U psi. Okay, that we have discussed just now. Now, how will you realize this U psi naught and U psi without affecting the information? Because we are not going to measure it. So when I discuss here, like, so when I bring in all the states here, I assume that I know all these states. But in practice, we don't know the states. Like, so when you do it in real time, we don't know who has the first rank. If you know the problem is solved, but we don't know. But there is a system which computes, which has that value. So system will take care of it, but we don't know it. So the system should take care of it. So how will we make the system take care of it? So that is the next part. So we have to know how to implement this U psi naught and the U psi 1. And to implement U psi naught, so this particular rotation, that is rotation with respect to psi naught axis. So what you can do is you can define an oracle which implements this particular operation. Remember, we are not going to measure F, so we are not going to see one by one. But this F is done within the system. Because of the superposition nature, it will act on every state, every roll number parallelly. So because of the superposition. Okay. So you apply this state and this will nicely flip. Whenever f of x is 1, that particular term will become minus. It adds a negation. And whenever f of x is 0, it will keep it as such. It won't give any value, any sign change. So it nicely flips. This flip happens nicely. Okay. So that's how we realize U psi naught by implementing this oracle. And this oracle uses the f of x. And there is now the second question is how will you realize U psi? U phi. So U psi can be now you have to somehow implement this U psi. So how can you implement it? So, but to implement U psi, you have to know this algorithm. So there should be an algorithm that translates the zero state, it need not be zero, some basic state, some known state, some known classical state into psi. Okay, so you should have some algorithm that translates uh, this some known state to psi. Okay, now you apply that algorithm. So you apply that algorithm, so that apply the inverse of that algorithm. If A is quantum, finding an inverse is easier. So you can always find a quantum algorithm such that A times 0 is psi, and then you can find A inverse. So A inverse times psi will be 0, right? Since A times 0 is psi, A inverse times psi will be 0. A inverse x is implementable. So A inverse times psi is 0. Now you flip only the sign of this 0. That is done by U0. U0 times x, that flips the sorry. U0 times psi, that flips the sign of this the zeroth state alone, like the state corresponding to 0 vector. And then you apply A again on it. So A times minus 0 will be again minus psi. And remember, this will flip only psi, and all the other states orthogonal to psi, they remain unaltered. So which helps us doing this flip. That is flip from this towards flip with respect to this angle. If this is theta, this will be theta. So this kind of flip. Okay. So this particular thing will help. This particular oracle will help you to implement that flip. So generally the entire quantum oracle is built on two oracles, like so two flips. The first one is U psi naught, and second flip is U psi, which is a combination of U0 and the U0 A inverse. Okay, and totally this is the single quantum oracle. Single Gruer's oracle. So one iteration of Gruer's oracle or one iteration of amplitude amplification contains these four operations. Okay, so that is the idea of amplitude amplification. So far any questions? Like, so I will stop here for some questions. Stop here for 1 minute for any questions. So I am stopping here because I have completed one classical algorithm. I have explained quantum amplitude amplification or Gruer's, a generalized version of Gruer's search. So I'm stopping here for some questions. If anyone have any questions, please feel free to ask. Okay, there is a question, I think, like, so whether quantum amplitude amplification is to realize the state alone. So quantum amplitude amplification is actually not to realize the state, but you are given a state, like you are given some psi. So from this particular psi, you wanted to find like psi can be written as something like this. Like, so if you go back here, if you see here, the psi can be written as a superposition of two states, two measurable states, like psi 0 and psi 1 can be measured because they are orthogonal to each other. So psi can be written as a linear combination of two states which can be separated out by a classical reader. Like, so for example, bit 0 and bit 1. So you can read out separately. So in that sense, psi 0 and psi 1 are two readable states. But then you have A times psi 0 plus B times psi 1, like that is the quantum state we have. But now you wanted to amplify the coefficient corresponding to psi 1, the amplify the value of magnitude of B. So that is the whole idea. Like, so so you do some amplification here, and the purpose of doing this amplification is once you do amplifications and you do measurement, chances of getting your result at psi 1 will be higher. For now, it is magnitude of B square, but if you increase the value of magnitude of B square increases. So you increase that this particular chances of getting value from something from psi 1. So psi 1 will be something of our interest. Okay. So I'm not sure whether I have answered the question, but yeah. So the idea is it's not to realize the state alone, like it is to like to amplify. So you wanted to solve a problem, so you wanted to amplify a specific states, and for that purpose. Okay. Okay. If there are no other questions, then I will move on to the second thing. So once the quantum amplification is done, we know how to amplify the coefficient of a single the region of interest, the interested state. Okay, and the second thing is the next problem that people look into is quantum amplitude estimation. So, and the problem here is you are given a state psi which is A times psi 0 plus B times psi 1, just like whatever we have discussed so far. And we have an algorithm A which translates this all zero. This zero for now it is a simplification of well-known state. It can be any state, okay, but it should be well-known because every time we have to prepare the same state again and again. If it is an arbitrary quantum state, we may not be able to prepare because we can't measure it. So, but if it is a well-known state, you can prepare it again and again. So it should be a well-known state, and algorithm acting on that particular state should give you psi. And the standard practices make it 0. Okay, so A times 0 is equal to your psi. And if you have this algorithm, now my goal is to find the magnitude of A square or magnitude of B square. Find the values of this coefficient. So earlier when I discussed, so one of the reasons that we have to do this is earlier when we discussed here, like when you discuss quantum amplitude amplification problem. So I mentioned that you have to run this n some order of B times, so order of magnitude of B times. But without knowing this magnitude of B, we can't do anything. So somehow we have to read the magnitude of B. So we can run this amplitude estimation algorithm first to understand the value of magnitude of B, and then we can run the amplitude amplification further. So that is one another strategy that people can do it in the search problems. But in some problems we know the B. So sometimes we know it that there are two students with rank 1, so we can nicely find the value of B by knowing psi. Okay, so that is the whole idea. Now the problem is to find A square and B square, and so this is slightly little deep into math. Like, so if you are struggling to get it, you can skip it. Okay, but the whole point is point you have to grasp here is you will I will give you an algorithm to find B, find magnitude of B square or magnitude of A square. That's the whole idea. And here what we people understood here is like if your state psi, this psi is a linear superposition of psi plus and phi minus, where psi plus and phi minus are eigenvectors of Q, that is Q that we find it here. Okay, for this Q. So your the arbitrary psi that we generated using the algorithm A, it is a superposition of eigenvectors of this particular operator Q. I hope you all know what an eigenvector or eigenvalue is. So if you do not know, just a simple thing is, if you have a state psi, and if you have a Q times psi, say psi plus, will be equal to lambda times psi plus, where lambda is a complex number, like it's not a vector. So if you have a operator Q acting on your state psi plus, and you get a scalar value outside, but the vector remains unchanged. So if you can have such a system, then we call lambda as an eigenvalue of Q. This is an eigenvalue of Q, and this vector, this psi plus, as an eigenvector of Q. So this is a definition of a simple definition of eigenvalues and eigenvectors. And now the idea is the psi, the state psi is a superposition of these two eigenvectors, psi plus and psi minus. And interesting fact is this psi plus and psi minus are eigenvectors with eigenvalue something like this. Okay, this should be minus I theta e. So here again there is a 2, like, so 2 is there, where I is a complex number. E power I 2 theta a and e power I minus theta a, where theta a is related to the value a and b, this magnitude of a and b. Okay, so maybe I missed out that relation. This theta, okay, it is here. So this magnitude of b star will be equal to sine theta a. So somehow, if we can measure these eigenvalues, if we can find out these eigenvalues, either 2 theta a or minus 2 theta a, if you can measure these values, then nicely you can find out this value. Whatever maybe, so whatever maybe, you either measure theta a or minus theta a, both will give you the same result here, because it is magnitude of b square, it is sine square theta a. So even if you apply theta a there or minus theta a there, it gets cancelled. You will get a positive number, right? So that is the whole idea here. So you somehow measure this particular value. That will be the goal of the next problem. The goal of this problem. Okay. So now we have something called a phase estimation. And if you go through this any standard quantum textbooks, they will have something called a phase estimation. Okay. So this phase estimation will solve this particular problem. That is, suppose you have a Q operator and you have an eigenstate of Q, that is Q times psi is lambda times psi, where lambda equal to e power I 2 pi theta. So if it is of this form, then this algorithm will give you a nice way to measure the value of theta. Okay, so that is this phase estimation problem. And now focus only on this. We can focus on the writings later. Like now, let us focus on this particular diagram. So now the whole diagram is, suppose I am trying to make you understand that theta can be measurable. So suppose you have this 0, like, so, and the state here will be like 0 plus 1. So this is Hadamard gate, which translates 0 to 0 plus 1 by root 2. So some people, so during analysis, I am ignoring that root 2. Maybe if you can think of this. So this particular point will be like this. And now you apply the control Q gate, so which is 0 times psi plus 1 times psi. And now if you apply this state to the control Q, what does it does like? So whenever the first value is 0, it won't do anything to the psi. So it will remain as 0 times psi. And whenever the first value is 1, it applies Q to the second one. So it applies 1 times Q times psi. So that is a function of control Q. That is a one way of explaining control Q. Okay. So now if you expand this particular equation, so what you get is 0 times psi plus, now here you may get a 1 minus 1 or directly. So if your psi is an eigenvalue, if your psi is such that Q times psi equal to minus psi, then what you get here is minus times 1 times psi. And this will be same as 0 minus 1 taking psi outside. So remember here we get a tensor product. I am ignoring tensor product for simplicity. Okay. So you get something like this. And now if you apply Hadamard on the first qubit, so this will become 1 and second one becomes psi. And now you do the measurement on the classical basis. So you apply measurement, and what you get on the first qubit, it is 1. It's a determinant. You have only classical state. So you get 1. So which means whenever you get 1, the so it is equal to saying that e power j 2 pi 0.1. So this is sorry. E power j 2 pi into 1 by 2. So if you have 1, this means this you call it as a by 2. This value of a will be equal to 1. So this will be same as e power j pi, and that is equal to -1. So this will be something like this. So you try to estimate this particular element, this particular number using this measurement value. Okay. So now to make it clear, now if you want to explain, say you have a quantum state like this, now you wanted to your eigenvalues, this lambda can be e power I 2 pi into say a by 2 plus a naught by 2 plus a1 by 2 square. So if you have a 2 qubit like, so it can take for different values of a naught and a1. If your eigenvalues will be of this set, one of these by changing the values of a naught and a1, then what you can do is you can expand the circuit. Your circuit can be something like this. Now what you get is from this circuit, you can get this value of a naught out, and from this expression, this particular circuit, you will get the value of a1 using the same logic that we use here. Okay. So I'm not going into the details. Maybe if you are interested, you can try it out. Okay. So somehow you measure a0 and a1 through this way, and then you can use this a0 and a1 to understand this theta. Theta will be of this form. Okay. So and you have 2 pi a, and you have some measured value of lambda, and you have some sense of measuring the eigenvalue. And what it says is the accuracy of this eigenvalue, the value of this a, which is this number, like this eigenvalue, this accuracy of this, it depends on this parameter, where m is the number of times you use q. So here you are using q 3 times. Okay. So here in this case, m is equal to 3. Okay. Oh, and the m can be changing. Like, so if it is of the 3 qubits, then m will be more like. So sorry, here it's 4 like. So m should be taken as 2 power 2. So there are 4 qubits. So m should be 4. So here m is equal to 4. Okay. And the m increases depending on the number of times, the accuracy that we want. Okay. And remember that this is accuracy in terms of the value of this a, this parameters. But what is the how confident you are? You say that this result is this much accurate is given by a probability, and it says that this is accurate to this level with the probability 8 by pi square. Okay, and that is the whole idea. Right? We have 8 by pi square, a probability constant. And now the whole idea of phase estimation is you can estimate the eigenvalues if you pass eigenvectors into the system. And the idea of phase estimation is you can estimate the eigenvalues if you pass the eigenvectors into the system, that is here. And if you apply the q square, say m times m is proportionate to this number of times you have to apply q and q square, and then you will get the result with this much accuracy. That is the value of the eigenvalue will be of this much accuracy, and with the probability this value 8 by pi square. And remember here your pi that you get it out is a superposition of eigenstates. So you can freely pass it through the system. You can pass that psi, and what you get here will be superposition of 2 eigenvalues. But once you do measurement, you will get one of 2 eigenvalues. So here earlier I mentioned you can either estimate theta a or minus theta a. Both eigenvalues are fine. So the superposition decomposes into one of either theta a or minus theta a, but you get something like, so from that theta a you can measure a, and the accuracy of that a will be something like this. Okay, that's what the phase estimation tells us. Okay, so far is it clear? Like so So the second algorithm that I focused is this amplitude estimation, and the amplitude estimation is to estimate the value of A or B, and you can use the space estimation. Like, okay, so I missed the term. Like, use the space estimation to get A or B with this accuracy. So in this case, I have mentioned it in terms of A. Okay, so you can get it with this accuracy. You can estimate the value of A or B. Is that clear? And with this probability. Okay, so remember so people may get confused because there is two versions of accuracy. One version of accuracy tells us that your value is within this bound, and another version of accuracy will tell us that how confident I am. So with the highest with the probability of 8 by pi star, my value will be within this range. Okay. So far, do you have any questions? Like, so now that what I have discussed is, given this state, like, okay, given some psi of this form, we can estimate the value of magnitude of A square or magnitude of B square with this accuracy, with this value accuracy, and with this confidence, with this level of confidence. Okay, and that is the whole idea of this amplitude estimation algorithm. You estimate the coefficient, magnitude of the coefficient. Okay, so shall I move on to the next thing? Like, the next thing is our quantum reinforcement learning. So these are two basic quantum algorithms, and which is applied in many other machine learning algorithms. So maybe in the second half you will learn machine learning algorithms. Even in machine learning, most of the machine learning algorithms, they rely on these two algorithms: this quantum amplitude amplification and this amplitude estimation algorithms. Okay, that's how they give the speed up. Okay, so any questions so far? Hello. Hello. Hello.
That's by mistake, I think.
Okay. Okay. Yeah. If you don't have any questions, I will move on to the next thing. Like, that is quantum reinforcement learning problem. So far, whatever we have seen is, like, we have seen an amplitude amplification part which amplifies the coefficient, and then amplitude estimation part which you can estimate the coefficient. Now let us try to move on to the quantum reinforcement learning problem setup, the problem that we focus on, especially that is mentioned in this paper. Okay, and the problem here is, so now my arms are quantum, like, so my arms are quantum, like, which does this kind of operation, which translates 0 to √3 times 0. So earlier, so this is nothing but so this is in classical sense, this is saying that my reward will be 0 with the probability 0.3 and 1 with the probability 0.7. This is the classical version of the same quantum oracle. And in classical sense, this is the reward statistics, and quantum sense, we model it in terms of an oracle. But the arm is something quantum, like, it's purely quantum. There is no classical arm here. Okay? And this can be applied in some computer simulations and learning some online games and so on. Okay. And now each arm has a different set of qubits. So each arm we will assign different set of qubits, so that whenever you play that arm, which means you run this oracle O1. Okay. So we play that arm, and then playing that arm is equivalent to applying this oracle O1. And remember, in classical algorithm, we play the arm, we get the classical reward. We get the reward. Now in quantum arm, we will not get the reward. Like, the reward is completely quantum sense. Like, it's a linear, it's a superposition of quantum state. We don't know the reward now. We are not going to do the measurement immediately. We will run it, we play it for some time, and then we do the measurement. That is how where we get the benefit. Okay. And now, so you do the arm, say arm 1 or arm 2 or arm 3, and based on the arm that you choose, you apply the oracle O1, O2, or O3 on that the qubit corresponding to that particular arm. Okay? So that is that's the idea of quantum setup. Okay. Now the goal here.
Sir,
Yeah.
for how long you'll be running that?
Sorry. Yeah, that's the challenge that we have to understand. So how long? So we have to play each arm, say, for n number of times, and that n can be reduced. So in quantum sense, to get an epsilon accuracy, you have to run, say, if it is classical sense, you have to run n number of times. In quantum sense, you can get it in √n number of times. That is the whole idea of this research. Okay. And how much time that I haven't talked about it now. Like, but now whatever I'm saying is, if you are playing ARM1, it is equivalent to apply this Oracle O1. If you are playing ARM2, it's equivalent to applying Oracle O2 on their qubit, their respective qubit, on not on a common qubit. Every ARM will have a separate qubit, and it is equivalent to applying this Oracle on that qubit. Okay, and now the simplifications of this problem, this quantum reinforcement learning, come from something called as quantum Monte Carlo simulation. Okay, and this quantum Monte Carlo simulation relies on two major statements. One is powering lemma, and another is this amplitude amplification we have seen just now. This part we have seen just now. It is called amplitude estimation. And there is something called as powering lemma, which is in classical sense we use it several times. If I know an algorithm A, which will give you an output A hat, output estimate of A hat, and with an accuracy of A hat, with the value accuracy of this value accuracy, and with the probability of greater than 0.5. If suppose if you have such a algorithm, if I know an algorithm A which can get my result within this range with with probability which is higher than 0.5, then what we can do is we can run that algorithm again and again, and we can improve the probability. The probability of that this A hat being close to A will be much more, we will be less than epsilon, with the probability 1 minus delta, where this 1 minus delta can be made as small as possible. It can be made to 0 to close to 0. Okay, but to achieve that, you have to run the algorithm roughly order of 1 by delta times. Okay, so if you run it order of 1 by delta times, then you can achieve this accuracy. You can increase the confidence of this result. So you can confidently say that my A tilde is close to A with an accuracy of epsilon. Okay, now in what does amplitude estimation says? I will get this result. My A hat will be close to A within this accuracy with a confidence of 8 by pi square. The confidence is 8 by pi square. So, and 8 by pi square, you can calculate it is greater than 0.5. So, which means you can apply powering lemma. So, you can apply the algorithm again and again. You can apply this amplitude estimation algorithm again and improve this probability. This 8 by pi square can be improved to 1 minus delta for arbitrary delta. And the value, the epsilon value will be something like this, which is close to this one, where t is proportional to the number of times you run the algorithm. Okay, that is the key catch here. T is proportional to the number of times you run the algorithm. So this accuracy and the epsilon value are inversely proportional to each other. So this so here t is number of times you run the algorithm. Okay, because earlier, if you remember in Grover's in amplitude estimation, when you discuss phase estimation, so maybe I have to erase all these things. So if I want, when we discuss the phase estimation, so with this parameter m, okay, so this page is nice. So this parameter m, in this case, for this example, I told 2 power 2 because I am using 2 qubits to measure it. I am getting the accuracy of the result using 2 qubits. So my m here will be 2 power 2. But for 2 power 2, the number of times you have to run the algorithm is say 1, 2, 3, totally 6 times. So that is like 2 into 3 times. Okay. And if I want to add one more layer, so if I want to add one more layer of accuracy, so I have to add q power 4. And remember, this is m becomes 2 power 3, 8. So here it will become 2 into 7. And it is roughly proportional to 2 into m. So it's order of linear in terms of m. Okay, but it's not exactly m, but it's m minus 1, but it's linear in terms of m. That is the whole idea. So this m, if you see, it is linear in terms of number of times you use your algorithm. In this case, it is 2m. So it's linearly proportional to the number of times you use the algorithm. So now what you can do is like using Monte Carlo simulation or using the powering lemma and the amplitude estimation. So you can get this this accuracy, this epsilon, inversely proportional to t, that is inversely proportional to m. So m is linearly proportional to number of times you use the algorithm. So epsilon, so that leads to this statement that epsilon is proportional to 1 by number of times you run the algorithm. Okay, so that's the whole idea. Like, so you can do it that many times, proportional to that many times. And then to improve this 8 by pi star, you have to run it some, if you want to improve this 8 by pi star to 1 minus delta, then you have to run big O of 1 by delta times, where delta is constant depending on this value. So this again becomes another constant. So it's again a constant times 1 by m. So it's still the proportionality don't changes much. It changes by a constant factor, but it does not changes in terms of the number of times you use the algorithm. Okay, so that's the whole idea. And the quantum Monte Carlo runs on this two steps. These two are the major steps. That is, they define a oracle W, which acts on your state X to this value. Like it gives you, it acts on state X and 0 to give you this value, where phi X is something that you wanted to measure. So where phi X is something that you wanted to measure, and then apply this particular thing to your Brewer search, this amplitude estimation algorithm with this oracle as W. Okay, that's the whole idea of Monte Carlo simulations in quantum version. So you can run it this many number of times, and you can get this accuracy sufficiently well enough. Okay, and we generalize this to quantum reinforcement learning. So quantum reinforcement. So far is it clear? Like the last step is just giving the algorithm. So now the algorithm should be clear, like roughly clear. Like so, using Monte Carlo, it is clear that you can get the accuracy of this much value, 1 minus delta. Like you can get the accuracy of 1 minus delta by repeating it in a proportional of 1 by epsilon times, where epsilon is the accuracy. So this is the epsilon value. So the t value that we get is proportional to 1 by epsilon times. Okay, so that is the whole idea of Monte Carlo simulations. So is it fine? But only one key point is we don't do any classical measurement in between. You do classical measurement only at the end of the time. So if you see here, you apply t iterations of amplitude estimation, and then you do the measurement. You don't do the measurement at the beginning. You apply it, and even here, if you see this particular picture, you apply Q again and again. You apply Q 2 times, Q 3 times, and then you do the measurement. You do something else here and then do the measurement. You don't do the measurement in between. Okay, and that is the whole idea of this speed up. Okay, so any questions so far? So I can stop for 1 minute for questions. So with this, I can conclude. The next thing is I will just summarize the algorithm, the quantum version of algorithm. Like so, this will give you a picture, give you an idea that it can be done. Like it can be done somehow, but only thing is how we make the flow, the final flow. That is the next part left. So any questions like? Okay, so if you don't have any questions, I will move on to the next part. Like, yeah, yes, any questions? Okay, if you don't have questions, I will move on to the next part. So the next part is just we have to conclude. We have to finalize the algorithm. That is the idea. So now what we do is like first we have. So earlier, if you remember this first part of classical RL, like so I can talk with this deterministic RL. Like so in this first part of deterministic RL, what we did. So we do not know anything about our arms. So what we did, like so we started looking into each of them. Like we started exploring them. So first what we did, we just go and see the arm 1 and get the reward. And then we go to the arm 2 and get a reward, and arm 3 and get a reward. Now we get an idea on how these arms behave. So the first part is exploration. And once we get the idea, now we fix it to the one that we get, which is higher in the sense. Okay, so that is called exploitation. So here also we do the same thing. And here, the first thing is you explore the each arm, say for n number of times. So ni number of times, where ni is the for the first iteration, ni is common, ni is constant for all these values. So Ni is constant for all the arms. So each arm you have to play Ni number of times where Ni is constant. So here Ri is set as 1, so Ni will be constant. Okay, where Ca is some constant. Okay, so you place it, you play the play each arm some Ni number of times to get a reasonably good accuracy. Okay, and estimate the value of mu I for each arm. Now for each arm you know the value of mu I. Now for each stage, now what you do is you set up IS, like you find IS which maximizes this value, like so which sorry. So you find the arm, like IS is nothing but arm. So you find the arm that maximizes the upper confidence bound, and this upper confidence bound is calculated by mu I hat plus Ri, where Ri is the term which helps us to find the it's the equivalent term for variance. Okay, it's not exactly variance. You will understand why it is not exactly variance soon. I will tell you that also, but it's not exactly same as variance. Okay, but it's some term, like some additional term that you add to make this confidence bound, like, to get an upper confidence bound. Okay, and every time once you play that arm, so the next time the chance of playing that arm, you have to give less priority to that arm because you have played that arm more number of times. So it is like you have played among two arms, you played one arm more number of times, which means you know more about that arm. The other arm you have played only less number of times, which means you know very less about that arm. So you should have a balance. You should not play too many number of times on one arm alone. You should not stuck on one arm alone always. So to make that, you change this RIS. This RIS. So this RIS can be decreased so that you reduce the upper bound. So the upper bound started getting reduced. Okay. So this RIS will be RIS by 2, and the NIS, that number of times you have to run that arm, will be calculated based on this value of RIS. Okay. So now you run this arm that you selected here, this arm IS, for Ni number of times. Play this IS arm for NIS number of times. This is the whole idea. The word I am mentioning, that play IS NIS number of times, depends purely on this quantum oracle. Like so, this groove search here in single Q, you are playing this arm twice. Okay, so Q square means you are playing that arm 4 times, and Q cube means you are playing that arm 8 times. So that's, and so on. Okay, so that is how you play that arm IS for NIS number of iterations, and then you repeat it for the every stage. And once that is complete, you go for the next stage and you try to maximize the IS. And in the meantime, so when you play this IS n number of times, here the one step is missing. So once you play this, you can update this mu hat. So this mu I hat will get updated based on this new results. So since you have played it more times, this value of mu hat will change. Okay, and this is the quantum version of reinforcement learning, under the reinforcement learning algorithm. And this is the algorithm. So if someone wanted to implement the algorithm and study the performance, they have to implement only these few steps. Okay, and so with this, I will conclude the introduction on the introduction on the quantum reinforcement algorithms. And what are the other problems that maybe people may be interested in to understand this along these lines, or these are some of the problems that we are also interested in. Like, so one thing is, like, there are other RL algorithms. So this algorithm, they focus on UCB, and there are other RL algorithms, something called a scale UCB and Thompson sampling and so on. And now we are interested to see whether there is quantum analogous for those RL algorithms, whether there is, and not all these algorithms are not based on finding this upper confidence bound. Nice thing like this. Okay, they are slightly different, and so we are working on how to understand those RL algorithms from quantum version. And second problem that I am typically interested in this is, like, the arm that we looked at in this particular algorithm are quantum arm. So which means in real time we may not be able to get this quantum arm, like whether this arms are practical. Like, can we make this more practical, this quantum arms? Or can we make a practical arm as a quantum arm? Can we convert a practical arm as a quantum arm? Those are some other questions that maybe people may be interested in. And the other thing is how to translate this algorithm into real-time applications. So you have the algorithm, now you can take your application and you can try to see how algorithm works in real-time applications compared to the existing algorithms in a classical computer. Okay. And with this again, I will, so this is kind of a reiteration of whatever I have told in the, mentioned in the last meeting. So just to start at short advertisement that, so this is my institute campus, like it's a beautiful place. And you can see it like here, like it's one of the most beautiful campus in the country. And so I work in the Department of Electrical and Electronics and Electrical Engineering here. And so mostly my research will be focused on communication engineering here, communication engineering in the sense. So I belong to the panel communication engineering, but my research will be focused on communication engineering, signal processing, and machine learning. So yeah, these are the things like about me, and these are the various types of topics that I am interested to do research or collaborate, or if anyone wanted some kind of training through internship or other collaborations, then these are the topics that I am interested in. I mostly, for now, I am mostly working on this quantum error correction course and quantum distributed storage and this quantum reinforcement learning. Quantum reinforcement learning. All these are like working with other people, as I mentioned. Okay. Yeah. Yeah. Now I will open. I'm open for questions now. So when I open for question, I would like to keep this page of my collaborators, like who helped me in learning this.
You can
Hello.
share any one of the practical application that introduce the quantum reinforcement learning and that.
So for the first thing is now the quantum arm. How will you see this quantum arm? That is a big question that is kept in front of. So this is much more interesting. That's why we started working or looking into it. But then when you look into this quantum arm, like, so how will you model that quantum arm? That is a challenging part. Now, if you have your arms as a system, like suppose you design a game, so computer games, like if you design some computer games, and if you are playing that computer game, then that computer game can model your actions in the form of quantum arms. So, uh, so when you develop computer games, these quantum arms can be helpful. Like, so they can model. They know how people. They know they may have some statistics of people working on, and based on that, they can develop a quantum arm, which computer may try to learn based on their based on the experiences. Okay, so that is one application that can come to the mind immediately. And so other challenging part here is how will you make this quantum arm into a practical, how will you make a practical arm into a quantum arm? So that is that is slightly that's a question that needs to be answered. Like, so I don't have an answer for now for that question. Because the users don't know this P of X. So other thing is like if you have a game of multiple users and everyone is playing the game, it's a game kind of thing. Rather than a real life thing, like if it is a game kind of thing where everyone contribute, they know the P of X and they choose it according to that random variable, then you can model each arm as a quantum arm. But other real life scenarios, since we do not know this P of X, it will be challenging to design this oracle. Like, so here our oracle. So when you think about this quantum oracle, so where did I start with quantum oracle? So here, so the arms are based on quantum oracle O1, O2, O3. And for to implement this O1, O2, O3, we need this statistics, that is 0.3, 0.1. But in real life, most of the real life scenarios, we do not know the statistics. That is a kind of a challenge that we are supposed to face. Like, when you don't have a statistic, can we model O1, O2, O3? That is a question that is not answered. Like, I don't have the answer for that.
How will you decide that how many arms you require for a particular problem?
It depends on the scenario. Like, so it actually depends on the number of actions we get. So so if I want to tell an example, if for example a student wanted to choose okay. So suppose if someone pedaling the cycle, then the different ways you can model the arm is like either you push the pedal towards left, sorry, push the handle towards left, push the handle towards right, or keep it straight. So there are two arms. So if I don't worry about the angle at which they push it, so there are three options. Like so in that scenario, you can think of three arms. Now, if I want to make it more accurate, then I can develop multiple angles. Like so, I can think of to turn left with an angle of 45 degree. Like I can make an angle of 45 degree, or turn left with an angle of 20 degree, and go straight, and turn right with an angle of 20 degree, and turn right with an angle of 45 degree. So we have five arms in this case. So we will the number of arms we have to choose depending on the scenario, depending on the game which we play, like depending on the scenario. And these arms can be continuous too, but for simplicity, we are now focusing only on discrete arms.
Can you say some of the challenges that you faced while doing this quantum reinforcement?
So challenges in the sense, so for now, whatever I explained is not our result. So whatever I explained is the result from this paper, like this people. So those are results from this people and these three papers. It's a merge of this result and this result. It's a mixture of all these three results. Okay. So our work is like kind of a very young child, like so. So we have just started, like so. I have interest. I am working in quantum computing, and so my colleague Dept, he works in. So his research is focused on reinforcement learning. So when we start, I don't know anything about reinforcement learning, and he don't know anything about quantum computing. So we started discussing, and so he wanted to learn quantum computing, and I wanted to learn reinforcement learning. So we started working together and started this problem. Took this problem, and by the in that time we got two students who are interested in working on this. So the biggest challenge, if you want to tell me, like tell the biggest challenges, like I didn't face much of challenge in terms of technical things. So in terms of technical things, um, yeah, I didn't give much of a challenge. So the challenge is like how we manage our time. That is how we face how we manage our time, how we manage our resources. Like so those are the places where we face the challenge. So for now, actually, Bapan is working on a different type of bandit problem that is more practical than this bandit. Like whatever bandit that I discussed now, and that bandit is not much of interesting. That paper is by so that is a paper. This is the paper. Like so, he is working on this paper which is based on quantum. And this is the first paper on quantum version of reinforcement. To our knowledge, this is the first version of this quantum multi-arm bandit problem. And so this is slightly different from whatever I have explained here. And there they unify all the arms together. And their algorithm is focused on choosing the best arm. Here, this algorithm is mostly focused, whatever I have presented here, this is focused on reducing this number of iterations you choose on an arm. Okay? So that is where this algorithm we chose. Here, everything that we focus on NI and how this IS and RS. And his algorithm, the quantum battery, that paper, that they focus on this particular problem. Like you have multiple arms, how will you choose the arm which has the maximum upper confidence bound or maximum value of average? Like so, there will be multiple arms, and this is useful only when the number of arms are high. So if you have 10,000 number of arms, then this quantum algorithm will be useful. Like this particular work done by these people will be useful. But in most of the cases, our number of arms can be restricted. But we struggle mostly in the complexity in terms of time, like number of trials we play and all. That is why we are started focusing on this particular problem.
Thank you, sir.
Yeah. So okay. Yeah, another slightly biggest challenge is human resources. People who are interested in to work on this intersection, like who can spend time on it, like yeah. Yeah. In technical sense, we didn't face a challenge now. We didn't solve any challenges now, but our challenges are this. So can we have more practical norm? That is one challenge. And how will you translate this into a real time? How will you translate whatever we have into a real time application? These are challenges we are working on. Now we are trying to solve. These are the technical challenges that we face, other than the administrative challenges I mentioned.
One another very general common question is if anyone is interested in starting quantum. So, is there any reference material or study material or any e-content?
So to initiate a quantum study, so what I will so normally I will suggest is like there is no like you have to pull out, like you have to work a little bit. So for any field when you start learning, it will be difficult. Like so there will be challenges. For any field, it is not restricted to quantum. If you are working on any field, when you learn it at the beginning, it is challenging. Even the English alphabet, A, B, C, D, like when we learn at the childhood, it is difficult. It's challenging. It's not that easy for a child to learn. Like, but the advantage of the kid is like they put more effort. Like they are happy to put effort. Like they are interested and they put effort on it. So that is how they learn it faster. Like that's why kids learn it faster because they are more interested on it to interested to learn it. So somehow as we go into adult, like somehow we lose that interest in learning, like that focus in learning. So once we get interest in learning, we can take all the challenges. Like, so any type of challenge we will take it. Like that is the first advice, like that I can tell you, like after facing all these challenges. And second thing is like for the books and also there is a textbook by Nielsen and Chuang that this is the textbook that everyone refer, like a textbook by Nielsen and Chuang, and I don't know whether I spelled Chuang right. And the textbook name is Quantum Computation and Quantum Information. So here, chapter 1 summarizes the entire thing well. So if you go through the chapter 1 and if you can understand most of the topics from chapter 1, it is well and good to start work with. Like then after that you can learn, you can choose the direction. It is just like you learn bits and now then you have to choose which path you want to do. Do you want to go to quantum communication or do you want to go for quantum computation or do you want to go for any other quantum information theory or do you want to go for quantum error correction codes or quantum estimation theory? Those things you have to choose later on. But for a beginner, the first step can be this chapter 1 of this textbook from the theoretical aspect, so to understand the theoretical aspects of it. So to start with simulation aspects, there is a course by an IIT Madras faculty, Prabha Mandhyam. So there's an online NPTEL course on introduction to quantum computing. And that will also be a good start so that they discuss more on this IBM's QUBITS, like so you can if anyone interested to start with simulations and they don't wanted to skip the math, they wanted to avoid this part of learning and they want to go from simulation perspective of learning and simulation perspective of research, they can start with this particular course. And there are many other courses where people discuss this simulations. This IBM especially, they made a very big advertisement. Like they made a very big a campaign on quantum computing. So there will be a lot of training programs you can available on YouTube regarding IBM's QuizKit. And this one is a formal course, like NPTEL course. So I normally prefer like a formal way of learning. So informal way of learning is not. I don't normally recommend informal way of learning. So formal way of learning, you can take this course and start learning it, or you can take this book and start reading the chapter one of this. You can choose one. Again, forget about the spellings. The spellings may be wrong. Like the name is Prabha Mandel, like, and here is Nissan and Chuang, like, but spelling there may be. I'm not very confident on their spelling. And Prabha Mandel is from physics department.
Good evening, sir.
Yeah, please.
Yeah. Actually, this is Arvind from Tech University, sir.
Please tell me.
Sir, I just have a query.
Yeah, tell me, please.
Yeah. Sir, what are the future challenges we have to face in quantum computing?
Oh, the first challenge is hardware availability. Like,
So
we
there
need
will
hardware.
be limitations of hardware. Yeah.
So now we don't have a hardware, like we don't have a full-fledged quantum computer. So we are in
Okay.
something called as so world is in something called as disk era. So this is called as noisy intermediate scale quantum computers. And these are like, we have a quantum computer, it may not perform well. So the number of qubits is very less, like 100 and 1000. It is very 1000 is believe me, 1000 is also very less. Okay, as long as it is noisy. So we have something like 100 or 1000 noisy qubits, like that is what we have. And with this, they use some strategy and get do some simulations, and some basic algorithms can be implemented, and the accuracy will be also like something like 70%, 60%. If they get 80%, that is a very good algorithm. So that is how the current scenario is. So if you want to get the accuracy with higher, close to 100% accuracy, then you need to go for large scale quantum computers with a full-fledged fault tolerant error correction codes and so on. So one of the highly like required field for this quantum computing is like, first is hardware development. So people who understand this hardware. And the second thing is, from theory side, most people like there is something called as error correction and error mitigation. So which I also work on. So we need more people to understand how this hardware can be, how these qubits can be protected from noise, and who works on the interface between theory and practice. So error correction is almost well developed. Like, so we have well established theory for error correction codes, but then how to make it practical, how to put it on the hardware and make it useful. That is the challenge that we will have it immediately after this. So first challenge is hardware. Like, first we need a qubit. The second challenge is we need to improve. You need to perform algorithms on the qubit with a reasonable accuracy. And there is another field also, which is called as quantum error mitigation. And this
Sir,
also
what,
will be, yeah.
Yes, sir. What about the security concerns, sir?
Okay, so from the quantum computer, so whatever I told is from the quantum computation perspective. From quantum security perspective, we have well-established quantum key distribution, which is one of the very classical applications of quantum computers. So people work on it. Like, so there are quantum key distribution algorithms, key distribution setups when people distribute it. So when I was doing PhD itself, we have a quantum key distribution of something like 100 kilometers and so on, like from IIT Madras. And we have other quantum key distribution algorithms from IIT Delhi, and so people from other countries also have working on this quantum key distribution algorithms, and it is almost practical. Like, so the people do it in practice. Like, so quantum key distribution, which can come into practice faster than probably it will be in practice now, but I am not very much confident about that. But that is the first practical thing that we will face. And the other thing is something. I'm not sure whether some people call this particular thing, post-quantum cryptography, this particular field is actually, many people add this in quantum technologies, but this is not a quantum technology, to be frank. This is a classical technology to defend quantum computers. So once quantum computers, if we have a full-fledged quantum computers, then all our security are under threat. So somehow we have to safeguard our information. Somehow we have to protect it. So people started moving into this post-quantum cryptography, which is purely a classical algorithm, but classical algorithm in the sense which the algorithm that can be implemented in a classical computer. But it is included in all these quantum related discussions because it is required to defend this quantum technologies. Okay. From security side, this will be of high, but this is well developed. Like we have standards also. This NIST, National Institute of Standards. I think yesterday I missed his name. Like so, yesterday the first day the other speaker might have talked about this post quantum cryptography. This NIST standards. So we have this. We have many standards that are developed for post quantum cryptography, and that is almost well established, and people are working on it. Okay, but there are some struggles in this post quantum cryptography too, which researchers are there like who are working on this post quantum cryptography, and I am also interested to work on it. For now, I am not working. Yeah, that is the security scenario with respect to quantum. And the quantum key distribution is the place where we secure the information, and that is not information security. We don't secure the information, but instead, classical security. If you are working on classical security, you may be knowing about this symmetric key and private key. Symmetric key and asymmetric key cryptography. And for symmetric key, we need something called a symmetric. For symmetric key cryptography, we need something called as private key. That is a key that is known only to the sender and the receiver. And this quantum key distribution will help us to share some private key. That is where it is helping. And it is, for now, it is not helping in protecting any information. Okay. And yeah, to make communication more
For
efficient.
this key, whether they are using any algorithms or something like that, because in the case of cryptography or encryption or something like that, we just use some keys in cyber security or something like that.
Yeah, so you need this keys, like, so maybe I will use this picture. So the idea is you send some quantum state, like, so someone will send 0 or 1 with the plus or minus. Okay, this is why I will explain one of the simplest algorithm that one of the basic algorithm, something called as BB84 algorithm. Like, so on quantum key distribution. So the users, they may send one of these 4 states. Okay, and they choose. So how they choose is, for example, if I want to send bit 0 or bit 1, so you choose one of these with uniformly probability 1/2 and 1/2. And then once you choose this, then I will choose either this or this depending on my bit. If my bit is 0, I will choose this. If my bit is 1, I will choose this. Then I will send that quantum state to through the fiber or to the user in the other end. So the other end will be receiving that particular state. For example, they may be receiving 0 or plus state if they send 0. But now the third party, to read that information, they should know this basis. Like they should know whether the user has sent this or this. They should know that information. So it is secured nicely. And now it reaches here. And then once it reaches here. Sorry.
Anisha, can you put everybody on mute?
Yeah. So once it reaches the destination, then they can reveal the state at which they have sent the information, send this particular information, either 0 or 1. And after that, they can measure it. But now only problem is some of the qubits in between, the third party may have accessed it and killed the quantum information. Like, so if you may send plus and they may have killed it to 0. They may kill it like, so there will be some disturbance. So whatever you receive out of it, and then they do some classical post processing, which is called as reconciliation. Oh, sorry. So I don't remember the technical term now. Like, but one is actually a error correction, which protects the correctness of the information, and then another one it protects us the. Oh, I think this is reconciliation, and another is
Yes, sir.
integrity. Like, so yeah, so another one is add another hashing kind of protocol. Like, so in classical sense, there is something called as hashing kind of things. So you add additional hashing kind of protocols to protect, to make ensure the key is secure, further secure. So you add one error correction protocol to reliably transmit the information between both the users. But then the product the key may not be secure, properly secure. So you add additional hashing protocols to make it more secure. So you add these two post-processing techniques and get a secure key distribution. Okay, and this is the algorithm, and most of the time this particular middle part will vary. Like this depends on the hardware availability. So they can do it. There are different protocols like cow protocol, and but I don't know much about all this technicalities. Those are more hardware-based techniques.
Sir, we just want to add some bit means in the case of hashing technique, it will be done, right? We just want to send the information from the source to the information by adding some bits. Yes, sir.
So yeah, hashing is actually do additional protection to the information. It will give you additional protection. You are not going to add more keys, but more bits to the keys, but you are going to
From the source side, we just want to add, and then
source side
yeah,
you have to send more number
during
of
the
keys.
time of
Exactly.
destination, we just skip the things, right?
Exactly.
Actually, this is a concept from error correction and error direction cyber security or something like that.
Yeah,
Yes, sir?
this includes the error correction too. There is an error correction part too, which ensures the reliability. So whatever they are sent from the sender side, it should be reliable at the receiver side.
Aravind sir,
Okay.
sorry to interrupt you. If you have few more questions, kindly please mail to Arun sir.
Oh, okay, ma'am. Thank you. Thank you.
Yeah,
Thank you,
sorry
ma'am.
to disturb you.
Okay, you can use my email.
Yeah, this is his mail ID. I'll WhatsApp in the groups.
Yeah, so one more point. I got one question through email actually. Like the question is like whether why should you encode bit 0 on ket 0 and bit 1 on ket 1? This is the question. Like why can't you do bit 0 on ket 1 and bit 1 on ket 0? This can always be done. Like this is an engineering problem. You can do it anyway. And some people may think of trying mapping bit 0 to bit 0 plus 1 and bit 1 to with 0 minus 1, and that is a different type of problem, which is a purely engineering problem, which is not like because of the science. Yeah, so if you have any other questions, yeah, let me know. Like otherwise, okay, so I will just finish it off. Like one more question is there, like to start working with error detection and correction, what are the algorithms and search methodology to start our learning? So the first idea is to understand what is quantum computing by reading through the chapter 1 of this textbook, whatever I have shared. And then after that, you can further navigate into something called the stabilizer codes, which is mentioned in the book. In the same textbook, they have that stabilizer codes, which is equivalent to our classical linear block codes. You might have learned classical linear block codes, which is one of the examples is Hamming code or the repetition code or error detection code. All these things can be shifted to quantum using that particular class of codes called as stabilizer codes. So if you understand that, then that translation will be easier. Yeah. So if you don't have any other questions, we can start.
Thank you so much, sir. First of all, I would like to thank from organizing committee side that irrespective of the last moment change, you cooperated with us, and we wholeheartedly thank for that. And regarding your session, yes, it was as usual, it was very interesting and interactive. And we learned about the basics of reinforcement learning as well as the quantum amplitude amplification and amplitude estimation algorithm at ease. And the way you explained the eigenvalue and eigenvector was added a feather on that entire session. And how this quantum is getting imparted in reinforcement learning is a thought-provoking, as we are very new to that. Thanks for taking this session, sir. Thank you so much for being with us.
Yeah, thank you for the opportunity. I hope someone get motivated to start working on some of the areas where I am interested on. So I hope it is useful and
Yes, I hope,
yeah,
people
the goal is to
contact-
motivate people and not to teach people on what are the topics there, like motivate people and so that they can start with. I hope the goal is achieved, or it is towards goal.
For those who
Thank
are
you.
into machine learning, they might have known that quantum can also be imparted, and hopefully we'll be getting much more mails from the participants. So on
Yeah,
behalf
thanks.
of participants and on behalf of organizing committee, I wholeheartedly thank you for being with us
Yeah.
for this wonderful session. Thank you, sir.
The final point is other machine learning also has a quantum analogous. Like quantum people started looking into other types of machine learning, like
Yes,
supervised
sir.
and unsupervised. But yeah, I didn't include them in this talk. Like I just focused on reinforcement learning because I started working on it.
Okay.
Yeah, thanks.
Dinesh, Anishar, can you please put mute for all the participants except the speaker and host? Dineshwar, are you there? Have you joined?
Yes, madam. Hello, you are able to hear me, right?
Yes, sir. Yes. I'll give a short introduction about the next speakers. So this is Dr. Ramagowda Dinesh from Samsung Bangalore. He's a very eminent person, and he work much more on image processing as far as I know, and I'm happy to know that he's into quantum computing as well. Dinesh sir is a principal engineer and head of A lab at Samsung Bangalore. Prior to joining this Samsung, he worked with various companies like Amazon, Honeywell, and HCL Technologies. He was a postdoctoral fellow at Seoul National University, Seoul. His area of interest includes image processing, pattern recognition, computer vision, and machine learning. He has over 60 publications to add to his credit in both international and national journals as well as in conferences. He has also have 27 awarded patent, and he's serving as an editorial board member for several reputed journals. He has been identified as reviewer for several international journals and conferences. He has served as a program committee member for several national and international conferences. He has successfully guided 6 PhD scholars, and presently 3 more are under him as a scholar. He has successfully guided many academic and research projects. He is a life member of IEEE, Computer Society of India, and Society of Statistics, Computer and Applications, International Associations of Engineers, Hong Kong. He is also serving a member of Board of Studies, Board of Examiners, and as an advisory committee for several universities throughout India and abroad as well. So I'm happy to invite him as a next resource person for taking the session on quantum machine learning, bridging quantum computing and AI. Welcome you, sir, and you can
Yeah.
the session.
Yeah. So,
Sir, you can
rather
share your
like,
screen, sir. You can share your screen.
Yeah, I'll share.
Happy to have you.
You are able to see the screen.
Sir, it is visible, sir.
Yes, sir.
Is it visible?
Yes, sir.
Yes, sir.
Yeah, okay. So, yeah, good evening to all. So first of all, before I start, I take this opportunity to thank organizers for giving me the opportunity to share my views on predominantly AA part, and then so towards the end, I will try to bridge. Maybe I just wanted to highlight the challenges in traditional AI or the ML concepts, and how possibly like because of the quantum computing can help us in overcoming these aspects. So that's the predominantly like because of the topic which I'll be talking for the next 1 hour or 1 hour 15 minutes or so. Yeah. So this will be the contents. I think probably I will just quickly run through the quantum computing or the basic concepts of quantum computing. Basically, you're already introduced into this maybe last few sessions. So I don't want to take much time here. Rather than I will try to highlight some of the key aspects of artificial intelligence, mainly from the point of machine learning, and I will try to also give like some of the potential industrial applications, so which various companies and the organizations are trying to solve at this point of time. So what kind of problem they are solving from the point of automating the various aspects using the machine learning and artificial intelligence. And so basically like okay, so highlights the potential of AI application in the current world. And maybe towards the end, as I mentioned, like so I will try to open up some of the bottlenecks or the challenges in traditional AI, or like we are solving those kind of problems using traditional computing approaches. And what could be the solution, like so how the quantum computing or the quantum AI bridges like we so try to bring the new perspective to solve the similar kind of problems of AI or the machine learning with the help of from the purview of the quantum computing. So this is what I just wanted to touch upon. As I like okay, so probably I always tell like so if you have any questions, you are feel free to stop me at any point of time, or even like so towards the end if you want to pose the question, that's also welcome. So I think if I try to compare like so the classical computing versus the quantum computing, I think this is the fair comparison, right? So in case of a classical computing, we always focus on the bit, and bit can take one of the two values, like so 0 or 1. So it is like even when you try to build this traditional circuit, okay, so either it is like so using your conventional gates, you try to either completely block or completely allow the information to pass through, so that like so your entire computation circuit is built on that logic actually. Whereas in case of quantum computing, I think probably by this time you are very well familiar. Like so, so we use something called qubit, a quantum bit, so which has got multiple states. So rather than from only 0 or 1, and there is a different level of uncertainty you can bring in. So that's the basic unit. And mostly like so the traditional computing model relies on the Van concept, so which process the information in a sequential order. So however you are trying to parallelize like so using the multi-threads or like so multi-processor environment, but information process within the thread or within the process set, it's always sequential in nature, because it traditionally follows the Van architecture. So whereas in case of a quantum computing, so it always uses the parallel mode of computing, so which essentially process the information at unparalleled like so parallelism, so which is very interesting and useful concept for solving the machine learning problem, which has got multi-ed. So today we are talking about the transformers, right? So where we need to get the attention. So these kind of parallelism definitely helps us in solving some of the very critical problems which requires huge amount of computational effort at this point of time. And so typically classical computing model, it can be a definite, and it can be in one of the two states, 0 or 1. Whereas in case of a quantum computing, so we have like so something called superposition, right? So you can have like so 0, 1, or it can be both state. Okay, so that's what like so the probability or the uncertainty which brings in, so which offers like so the a computation, a new paradigm of computing, where like so information can be like so not only at the present or urgent level, like it can be at intermediate levels actually. And so with respect to the speed, like okay, so typically the classical computing is limited by physical components, and again like so it is governed by the Moore's law, right? So like typically after certain physical boundary, the number of transistors or the gates you can fit into a unit area is the limit actually. Like so beyond that, you won't be able to fabricate or like so improvise your chips. So though you can bring like some more number of chips and you can connect them, but one of the problem in doing those kind of like so parallel connection is, so there will be a lot of overhead, and the data transfer between like so these multiple computing gates which are connected through the bus are like so different interface layers, right? That could become bottleneck actually, even in spite of like so you are trying to improve your overall performance uh, by having more number of components. After some time, you won't be able to get that expected throughput even by connecting multiple computing gates. So that is what like so people are foreseeing, and end of the traditional computers. Traditional computers are doing good, and to extend like so we are trying to improvise overall computation performance. But after some time, so where our computational demands are keep on increasing with the exponential rate of data growth. So the kind of problems are like so can be solved with these kind of traditional or the conventional computers to address the ever evolving the newer kind of problems, right? That becomes a limitation. So that probably like so which is expected to be solved with the help of quantum computing. Again, like so there is a uh, today as we are talking, so quantum computers are still like so not fully realizable. Like so still they are at very infancy stage, but the theoretical concepts has proven that like so it can potentially overcome some of the limitations, but it has to be like so realized, and it has to be experimented, and lot of algorithms need to be rewritten. Like so whatever the conventional algorithms we have like so which we have written, which we learned, evolved, and experimented and developed to solve the current problems, right? So to even to transfer those algorithms, even to transform those algorithms, or like so to translate those algorithms to be solved using the computation quantum computing requires a lot of effort. So this is where like so there is a potential research opportunity, and so good synergy for exploring and building these kind of technology. Like so no doubt, I think probably even recently Nvidia and like so the global three, right? Google, IBM, and Nvidia. Like so they jointly announced that okay, so the power of combining AI and quantum computing, because people started realizing that okay, so the amount of problems which we can solve through the classical computer, like so typically the ML problems with the conventional or the classical computing models are slowly becoming like okay, so reaching the threshold. So now what next actually, how we can prepare ourselves to solve a different kind of problems which can start emanating. Like okay, so today we are talking about a different level of artificial intelligence, right? Probably I will touch upon like so there I have a specific slide to talk about different level of artificial intelligence at the later stage. So these kind of problems can be solved effectively, is expected to be solved. Like so nobody knows how far we will be successful, and how much throughput we get it. So but theoretically it has been proved that okay, so these quantum computing are effectively able to overcome some of the potential challenges which currently the classical computers are staring at. Okay. And so from the application standpoint, like so the broad range of tasks are able to solve using the classical computers. But when it comes to very specialized tasks, especially like so the complex simulations, Okay, so one of the classical example of classical simulation is like, so today we are talking about, so currently like, so industry 4.0, if I just to touch upon like the industry 4.0 is basically like, just like computers undergo like with a different evolution, right? Even the industry manufacturing sector has undergone like with a many evolution. So we started with industry 1.0, where like, so the industrialization started happening, like so people started building the machines and mass production. And then like, so then came like the industry 2.0, where like, so the machines become like, so little more versatile, and they can start producing more number of input, like so the products using the basically like so, the industry 1.0, or the very initial machines were the steam powered. Then came like so the electric powered machines, and industry 3.0 like so basically mass expansion and like so training the people, and like so then came the CNC and other kind of things. But all this generation has got like so limitation, mainly in the terms of the experience driven process. So there people started moving towards the industry 4.0, where like so the primary focus was on the data driven industry manufacturing process rather than the experience driven manufacturing process. So today like, okay, so with the classical computing, and also with the help of machine learning and the data science and artificial intelligence, so Industry 4.0 like so was very very successful, and in fact that is the one aspect like so where we are seeing like lot of industries are getting automated today. Now the next generation of industry automation is like, we call it as a uh, performing the manufacturing setup even without like so setting up the factory. So that's where like so the digital twins are coming into picture actually, where I want to replicate the manufacturing machine using the simulation process, where I can build, conduct all the experiments, identify appropriate. See, basically in any manufacturing sector, right? So you need to set up a lot of parameters to set up the machine, manufacturing machine, even before you start producing a single product. And this recipe prediction, we call it as a recipe prediction, recipe setting. And this recipe setting is always a manual process, like so it is a trial and error process. In this trial and error process, it can take quite a amount of the human effort, and also like a lot of consumption of raw materials, and your industry or your machineries will be idle in while performing this kind of trial and error operation to come up with a optimal recipe. And all these things can be overcome with the help of the digital twins. And these digital twins require like extensive amount of simulation. And today, so simulating that kind of the entire manufacturing setup, entire manufacturing line to the precision and to the granularity level, like so at the very component level, is always a very very challenging. And the traditional computing systems can pose like so very significant challenge there. Either you need to have like so more number of servers to deploy those kind of solution, to build those kind of solution, so which is a huge amount of cost. And even with that kind of connecting too many computers together, you may not still not be able to achieve that kind of throughput. So that's where like so these kind of quantum computers which are very very specialized, so powerful to solve the specific task like with simulation and optimization problems, is very very useful. And this is one of the area like okay, so where there is a high degree of synergy, and like so lot of jobs can be created. And even like so industries are like so very very eager to invest and solve these kind of problems. So it's not so if you take any manufacturing industry, they don't want to perform the trial and error based kind of. See now factories are smart, so there is a lot of sensors mounted, a lot of data being collected. But the question is how best we can utilize this data and then perform these experiments on a simulation model. So by building a digital twins. So this is one of the potential application where like so quantum computing is expected to revolutionize the manufacturing sector itself. Okay, so with this, like, let us move on. I think probably I will just quickly skip this. I think you already know what is quantum computing. It's a so one thing I just want to stress here is like so quantum computing is not an improvised model of a traditional computing. It's altogether a different model. So one should not think that okay, so we had a different evolutions of computing systems, right? So like different architectures and like so different levels of processing the number of bits. It's not about like so, trying to compute more number of unit operations in a unit time. Okay, so please don't misunderstood. So quantum computing is not to build, not it is not being built to perform or churn more number of operations in a unit time. It is altogether different way of computing itself. Actually, like, so that's the one thing I just wanted to highlight. So these computation models, like so using the quantum theory, so they are expected to be much more powerful than the conventional models. But the catch here is, so this is at the very infancy stage that we have to understand. Like so, currently mostly whatever the problem we are solving through the computing models, right? So it's mostly solved through the simulation models, and we don't have a full-fledged computing quantum computing models available yet. But because of the potentiality which has theoretically it has shown, and some of the experiments conducted are the kind of data it has shown, right? So there is a huge potential. So which requires people to start looking into it and trying to start taking and addressing some of the critical issues and build this kind of system. So once these are built, I think probably like because of the kind of opportunity it will create is unimaginable. Okay. I think these are some of the just to show how some of the traditional problems, like so, which we call it as a NP problems, right? Non-deterministic polynomial complexity algorithms can effectively be solved using the quantum computers. So, if I finding the given a number n, finding like so what kind of factors like so p and q will generate that number n, right? So even with the traditional algorithms or the traditional computing model, the best possible algorithm is of the order 2 to the power of big O of n to the power of 1 by 3, which is a non-deterministic non-polynomial algorithm. And these kind of problems can effectively solved using a quantum algorithm in a quadratic time complexity, like so, which is a polynomial time. That means there are already some efforts and some the POC or the some kind of theoretical study has been shown. Some of the non-deterministic complexity algorithms are which the classical algorithms takes non-polynomial time complexity algorithms can effectively solve using a quadratic time or a polynomial time complexity algorithms. Okay, and this is another quite interesting. Like so, to find if there exists a I for which xi is equal to 1. So to just to find which bits are 1. So typically this algorithm requires one complete scan of this input range and input sequence. Whereas like so the equivalent quantum algorithm can solve this problem in a big O square root of n, which is fraction amount of time which takes in a classical computing. Okay. So similarly, like so, cryptography is one area where like so the quantum computing has given like so significant amount of input, the contribution where like so we can have a like so better encryption and encryption about the data. So data security is ensured. So using the quantum algorithms. All right. So these are the some of the cases I just wanted to touch upon, like so just to show you that the power of the quantum computing. Now let us like so before we look into like so the limitations or like so the challenges of that current classical computing model, mainly from the point of AI. So let us try to quickly run through like so what is AI and what kind of problems can be potentially solved today with the help of AI technology, and why where we are staying, like, so the we are hitting the threshold, and then probably we will start addressing about, like, so what kind of quantum technique can be effectively solve those kind of the threshold points and expected to solve. Okay, so I think from artificial intelligence point of view, like, okay, so if I define AI in a very simplest form, so it is nothing but, like, so okay, you are trying to mimic the human intelligence with the help of a machines. So as a humans, we get the inputs from various source. So through our sensory organs, five sensory organs. So just like that, so even the artificial systems or the artificial agents will try to get the inputs from various sources. It could be like, so data stored in your databases, or data coming from your sensors, or images captured through the cameras, etc. and so forth. Okay, so data can be multiple source and multiple ways from where you can get the data. And this artificial intelligence agent consumes this input data and try to provide output in terms of actions, movement, or in the text. Okay, so action means, like, just like, okay, so human brain, when you see a tiger, what kind of action, like, so brain will suggest, like, so either you try to uh, run, freeze, or like, so similar kind of thing, right? So even like, so depending on the input data, agent will try to suggest what kind of action has to be done. Or if you are building a robot, it will try to define, like, so what kind of movement has to be done, like, so whether it has to move in the forward direction, it has to move left or right to avoid the obstacle. And sometimes the output could be in terms of the text, where, like, so the text could be like, okay, so suggesting the business model for you, or like, so predicting the temperature, predicting the rainfall, or like, so predicting the outcome, etc. and so forth, right? So basically, like, okay, so it's you will have, like, so the some agent here, so which agent is expected to be a artificial agent instead of a human. So just like, okay, so your human sensory organs, like, so we have a different means from where I can fetch the data. So this agent will consume this data and try to give the output. But only difference here is, like, okay, so this agent is not using any traditional or a conventional algorithms, rather than it is using some kind of intelligence in solving the problem. That means if I give the same data, next time the output could be like, okay, so it's not the same output. It is the output is evolving over the data. That means the behavior of the algorithm expected to change over a period of time over the data as it consumes the data. So that's the only difference between your traditional algorithm and the intelligent algorithm. Great. Okay, so this is what I was referring. Like, so today we are talking about different levels of intelligence, especially artificial intelligence. Okay, so we have just like, okay, humans also can be classified into a different level of intelligence, right? Even the artificial systems also can be created in a different level of intelligence. One is artificial super intelligence. So artificial super intelligence is an intelligence where this artificial intelligence system can oversmart humans in almost all aspects of life. Getting the point, right? So it is, no doubt, it is an intelligent system. It's not only intelligent system, it is expected to oversmart humans in all aspects of life, not in any specific task. It is in all aspects of life. So now the question is whether these kind of systems are existing today. So no. So these are like, so there is a kind of researcher, as a research is happening in this area, but artificial super intelligence is not a reality at this point of time. And I think if you're actively following the trends in artificial intelligence and the development activities in artificial intelligence, probably you might have heard, like, so NVIDIA CEO, Mr. Hong, uh, Jensen Hong, has mentioned that, okay, so artificial intelligence could be a reality maybe by 2028 or 29. So we can start seeing some kind of artificial super intelligence systems available in the market by that time, and maybe in 5 years down the line. Okay, so that is the highest level of artificial intelligence, like, so one can envisage. The next level of artificial intelligence is artificial general intelligence. Artificial general intelligence is these intelligence systems are similar to like so most of the traditional like so these are the intelligence system which can perform the task on par with any humans actually like so just what we are trying to achieve possess the intelligence, right? Human level kind of intelligence. So these kind of systems can perform the task. Like okay, so these systems could be like the intelligence system could drive the car and then clean the home and make the decision. So just like okay, so the humans, right? If you take any particular person, the particular person can perform multiple intelligent tasks. He can drive, so which definitely requires some amount of intelligence to make a decision about when to accelerate, when to apply the brake, okay, what direction it has to be moved, etc., and so forth, right? So at the same time like so the same person can like so read and comprehend, so he can cook and he can play, so that means yeah say any normal human beings can perform multiple tasks, so which involves intelligence in the similar direction. So these artificial general intelligence systems can perform multiple tasks, not at the superhuman level, at least at the on par with the human intelligence level. Okay. And again, these systems, as on now, today we are talking, these kind of systems are not available in the market. Of course, they are at the very, very advanced stage of the research. And again, going by like so the NVIDIA CEO's recent commentary. So these kind of systems could be reality maybe in 2025 or 2026. That means in one less than 1 year or about 1 year, we will be able to see this kind of artificial general intelligence system, artificial system which can perform, which can match the human intelligence at multiple activities. Whereas, so we are like so another level of intelligence is called artificial narrow intelligence. And I think probably like so this we are all using it knowingly or unknowingly today. So these are the systems which are categorized as machine intelligence, right? Okay, or the machine learning, which are the system built to solve specific problems. So these are the systems which can intelligently work and achieve like so much superior result than the humans in a specific task. For example, if you build a machine learning system to read the handwritten numerals, so these systems are like so very very good, and it can outsmart humans in reading the even the worstest possible handwriting numerals of the characters. Okay, so similarly, like so the playing a chess. I think probably you might have seen like so the computer programs or the intelligence, the computer programs are beating the grandmasters. Okay, but whether this system can solve other problem, probably no. So they are the system, they are the intelligence systems built to solve specific problems, which we are already like we so using in various aspects. So like we so that is already a reality, and knowingly or unknowingly, we are already using. Okay, so just to summarize this slide, so we have a different level of artificial intelligence, like so are the types of intelligence. So artificial super intelligence, general intelligence, and narrow intelligence. Moving on, like so, probably artificial intelligence or the machine learning is not new. Okay, probably this was existing like so last almost 5 decades now. Now all of a sudden, like so machine learning or artificial intelligence become very buzzword very recently. Like so, probably um, uh, if you are a end user and using only AI, probably you might have started hearing AI about in the from 2021 or onwards actually. Like so, if you are a serious researcher or like so, if you are studying about artificial intelligence, probably you might have started studying about artificial intelligence or the machine learning, maybe uh, some kind of algorithms, maybe in 2010, 11, 12, that kind of time frame. But so though like so it was existed in the last 50 years, but why all of a sudden like so the machine learning came into forefront, and what made it so popular is one of the early recent paper like so published in the area of deep learning. Like so earlier, so we had a neural networks. we had machine learning, lot of machine learning algorithms, but the amount of problems we could able to solve with those kind of algorithms were very, very limited. Okay, so and still it requires a lot of knowledge with respect to the domain expertise. You need to handcraft the features, and you need to decide what kind of features you need to do extract. You need to map it. All these things were like so a very, very manual and very tedious jobs. And this particular like so the paper like so on the deep learning so change the overall perspective of like so the kind of problems or the areas where like so AI can penetrate. Okay, so there were like so two activities I would say like so there was a lot of developments happening in the area of the IoT, okay, and the sensors where like so we made like so the lot of sensors available to collect various type of data, and at the same time like so you have like the advancement in the mobile computing like so where like so your mobiles are started becoming very smart where like so it can have multiple sensors involved like so the GPS, the accelerometers, etc and so forth to track your direction, your GPS, your location. That means you started generating enormous amount of data even without your notice. That is one aspect. That means like so you collect there is a exponential growth of data generation, and there was like so this development in the area of deep learning where like so you need not to worry about like so handcrafting the features, and you all you need to focus is what kind of problem you need to solve. What is the problem that you are trying to solve? That problem you need to define. Data is already available, like so exponential data is available. Now, how best we can fit this into a purview of like so the computing. Okay, so that's where like so the machine learning or like so your artificial intelligence becoming start more simpler, and at the same time they become more powerful to solve most kind of problem. So if you look at the traditional machine learning, right? So this was the problem. What was the problem is, so you need to collect the data. Anyway, you need to collect the data even for the deep learning model. But one of the major problem or the bottleneck in the traditional machine learning algorithms compared to deep learning algorithm. I'm just trying to compare with respect to the deep learning and the machine learning. So you are expected to, it's a human or the expert, machine learning expert or the data engineer is expected to extract the features. So which requires, so if somebody is working on a medical domain, he also need to know about like, so not only like so the knowledge of machine learning, he also need to know about so the terminologies and like so the how to interpret and how to read the medical data. So similarly, if somebody is working on industrial data, he has to understand like so the from the point of industry standards, what kind of data, how to interpret the sensor data, etc. and so forth. And then he has to choose the classification model, and then he has to train and get a model. But so one of the major challenge or the bottleneck was this handcrafted feature extraction. So deep learning tried to overcome that problem of like so this oh, so it will try to have like so more number of layers, the hidden layers, which transforms your input data into a so data representation. So where like so your the task specific features will be learned through these deeper networks, and once the task specific features and the data specific features are learned, so this will be given to a classifier, and then it can be done. And all these things can be done without any human intervention. All you need to focus is like so develop like collect the data, select the appropriate architecture, and the rest of the things are solved. So that's the beauty of this deep learning. And because of this inherent simplicity of this workflow, where you need not to worry about like so the supporting the multiple domain. Okay, so this made so the entire the aspect of artificial intelligence, especially like so when I say like so I am interchangeably using the artificial intelligence and the deep learning or the machine learning. So here when I'm talking about this learning aspect, right? So I am talking about the artificial specific intelligence, like so the not even the narrow intelligence, specific intelligence. That means so even before like so to solve that specific problems, you need to have a specific domain expertise. Okay, that's what like so this deep learning is trying to overcome. Like so, you need not have you need not to have that kind of domain expertise. All you need to do is collect the data, select the architecture, and rest of the things will be taken care by the algorithm itself. So that's the beauty of deep learning. And because of this inherent simplicity of this entire architecture, right? Many people, many researchers were attracted to this kind of paradigm, so which exponentially showcased, so produced the results which catch the attention of multiple people, like so at the multiple business leaders, so that they took up these things and they wanted to embrace the beauty or like so these algorithms to solve their day-to-day problems actually. So that's where like so it started with deep learning, and then like so it gave birth to CNN, and then like so became the transformers, and the transformers led to your GPT models, and today we are talking about like so the chat GPT and like so RAG. So the things are innumerable. Like so now everybody is relying on like so generating that your responses or your you just post the query, and like so these GPT models are like so your RAG models are expected to give the answer for all kind of problems what you are having. Of course, like so we have a still like so the models are evolving and the quality of results are getting improved day by day, and there is no doubt like so the already like so the kind of result being generated by this kind of GPT or the RAG models are like so is quite impressive, and people are completely relying on these kind of systems to make a plan, make like so the business decisions. So various problems can be solved. I think probably I'm sure like so each one of you might have already experienced like so using the GPTs and the RAG for most of your problems actually, to so come up with a solution for your problems, right? Now, let us try to quickly see like so. I think again this may be like so of more interest for people who are doing research in the area of machine learning and the deep learning. Still like so, the question the graph here shows that like so. Uh, is like so the traditional machine learning is dying or like so still is useful, or like so when to go for traditional machine learning algorithms or when to select the deep learning algorithms. That's the kind of answer like so this graph suggests actually. So you can see like okay, so this graph the x-axis is a data axis, so that means like so the size of data, and the y-axis gives the performance. Now what you can infer from this particular graph is multiple things you can infer. One is uh, you can see like okay, so as the size of data increases, the deep learning algorithm performance increases drastically, whereas like so your traditional machine learning algorithm performance is almost stagnant. And the question being asked is why do you see this kind of thing? Like so, any one of you can would like to give the answer for this? I just wanted to pose a question here is why do you see like so in spite of see in any machine learning algorithms we say like so as the data size increases the your performance is going to increase, but in case of a traditional machine learning algorithm, so even if you say your data size is increasing, the algorithm performance is not increasing. It is almost becoming stagnant. Okay, and whereas in case of deep learning, as expected, like so, it is improving. So can anybody want to tell me like what could be the reason for the performance of traditional machine learning algorithm is not increasing with the increase in the data size?
Future extraction.
Okay. All right, like so due to the limitation of time, let me give the answer here. So the reason here is so in case of a traditional machine learning algorithm, so your features are handcrafted, right? So even though your data size is increasing, So since you already fixed the data, the kind of features you want to study, okay, you have decided what kind of features you are going to use and what kind of what are the ranges for those features, right? Already pre-crafted. That means already pre-decided, and you extracted those features. So though your data size is increasing because your feature extraction method is almost finalized, or there is no you are not further refining your feature extraction method. So the traditional machine learning algorithm performance may not significantly improve as the data size increases. Whereas in case of a deep learning model, so your the feature extraction is not fixed actually. So the algorithms are expected to learn the features with respect to the data. So that's the reason, like, so we can see, so there is a significant amount of increase in the performance as the data size increases. Now the question is, then when to use like so the traditional machine learning algorithm? So do we still have the scope for using those kind of traditional machine learning algorithms in our day-to-day life or the real-time applications? The answer is yes. So if you are working on a problem where data collection is very, very challenging, like so the amount of data you are going to collect is severely restricted because of the non-availability of the data, or it is very extremely difficult to collect the data. In that case, it's better to go with learn about the domain expertise and try to model it using conventional machine learning algorithm, or the situation where your problem is simple and you have like so the complete knowledge about the data and the data tendencies and the distribution of the data. In that case also you need not to strain yourself and overfitting your algorithm for a simple problems actually. In such cases it is better advisable to use a traditional machine learning algorithm over the deep learning algorithm, right? So this is the interpretation. There are multiple other things can be inferred from this graph. So let us not get into the too detail here. Okay, I just want to take up the example of a supervised learning, and just to show you like so what could be the problem with this deep learning model and the computation. How crazy or how awkward this problem can look like. Just to highlight that one, I have taken this particular example. Say I have this image. My problem is very, very simple. Given an image, I want to build a classifier which tells whether this is a outdoor image or an indoor image. That's it. Very, very simple. Very simple type problem I have taken. Okay. So given an image, so the expected output is whether it is an indoor image or an outdoor image. That's it. Okay. So now let us say like so if you look into the pipeline of machine learning, so given if I talk about the traditional machine learning algorithm, so you need to extract the features. So again, the question comes here like so what kind of features you will extract? So you should have some kind of knowledge. What kind of knowledge you need to have? So if I am talking about the indoor condition, indoor scenes, what kind of patterns or what kind of features I can see? Like so whether it is a kind of lights or kind of a luminance I get in the image, or kind of a regularity in the patterns present inside the house or outside the scenarios. So probably using those kind of, I will try to design like so what kind of feature engineering I will try to, and I will try to define like so those features. And then, so once you have a feature extraction is done, then you train the classifier. Whereas in case of a uh, deep learning, you will have the same kind of problem. So you have an image. So here, like, so you will have a multiple hidden layers where you try to extract the low-level features and then mid-level features, high-level features, and so multiple level of feature learning can happen. You need not have like any kind of domain expertise, or you need not to analyze the problem. All you need to do is provide sufficient amount of scenarios and the scenes to arrive at like so the feature learning, and then of course you will have a trainable classifier which is similar to in the previous case. So this is where the feature learnings happen, and this is where like so the training happens, and finally you will get the output. Okay, so this is how like so the response looks like at the different level. So at very low level features, you will have like so very raw edges, and then in mid level like refined edges, you will get it, and then in the very high level, you will have like so the kind of a patterns. Okay. So now these are my features learned. So you will have a different patterns for an indoor scenario and different patterns for the outdoor scenario. And these are the features which has been extracted or learned. And these features will be given as a trainable classifier, and your classifier will try to classify whether it as a input or output. At this point of time, I just wanted to bring one more quick concept here. So why deep learning gained a popularity? Why deep actually? Like okay, so there is a one simple experiment has been done. Like so, the experimental study has been done. How the deep learning models performs better compared to your traditional machine learning. So the problem is like so given a signal or the speech signal. So here they wanted to study the word error rate. Okay. So as the number of layers increases, you can see like so the word rate error rate has come down actually. Like so initially the each one there is only one layer with the 2000 neurons and the error rate was 24.2%. And as the number of layers increases, the same number of neurons. So you can see like so there is a significant reduction in the error rate. Okay. So this is what the study, empirical study, not the theoretical study. But on the other hand, there is a theoretical study called the universality theorem, which says that if you take any continuous function f, okay, and which is of the form f mapping from r to the power of n to r to the power of n, which is a very, very classical machine learning problem. Okay, I will tell you like, so what is this actually? That means I need to find a function f which can map n-dimensional real numbers, a real vector, into a m-dimensional real vector. So what is this n-dimensional real vector? It could be like, so you probably for a given instance, you might have extracted n number of features, right? Okay, this is your feature space. For a given pattern, you have extracted the n number of features, and I need to classify into m number of classes. So which is a classical machine learning problem. Okay. So universality theorem says if you take any function which is a mapping from r to the power of n to r to the power of n, which can be solved by a network with only one hidden layer. Okay. So unlike okay, so the deep network, right? So it says that okay, so if at all you want to solve the problem of this form, so only one hidden layer is good enough. So you need not have a deeper layers. You need to have only one hidden layer. So if you have one hidden layer, this problem can be solved. But the only question is, you should have enough number of neurons in this one layer itself. That's what the universality theorem. And you can find a simple proof also. Like okay, so what is the universality theorem of this one? So this is the condition. The only condition is given enough hidden number of hidden neurons in a single layer, so any problem can be solved. Now the question is, just for the sake of simplicity, I call this kind of network as a fat network. Okay. So now the question is fat network versus the deep network. The fat network, so where like so only one hidden layer with the more number of neurons. So there is a theoretical proof. So in spite of that, the fat networks are not very, very popular. So whereas the deep networks are very, very popular, mainly because of the fact that, okay, this deep network brings in the fact of the modularity, unlike the fat network. And training this fat network, like, so you never know like how many number of neurons need to be added. So because of all these challenges, so people prefer to use the deep network over a shallow network. So that's why like so the deep networks are producing much efficient result. So it doesn't mean that okay, so this cannot be solved using a shallow network. It can be solved, but the challenges involved are the interpretability becomes very extremely difficult in case of a fat networks over the deeper networks. Okay, so that's what caused like so this the deep networks a more popular case actually mainly from the because of the modularity, and it is easy to interpret and explain so with the help of a deep network. Oh, so given an image, so if you have like okay, so deeper network, you can always classify, like, so first you can train one classifier to classify whether it is a girl with a long hair or short hair, right? So you can have a only first level of classifier to classify whether it is a boy or girl, and another classifier to next layer to classify the next level. Okay, so that way the modularity can be envisaged or ensured with the help of a deep network, but the same modularity or the interpretation could be difficult with the help of a fat networks, right? So you got the concept, like, so why the deep networks performs much better, even though we don't have a sound theoretical background or the theoretical proof to ensure that, okay, deep networks are the best. Okay, so the main reason is the convention, uh, just because of the convenience, right? Convenience of the developing the architecture, and also, like, so the convenience of explaining and interpreting the results at the multiple layers, right? So that's why, like, so the deep networks outperforms, or like, so the took the driver's seat in the development growth of the artificial intelligence at this point of time, right?
I have one question.
So another problem is, I will just skip this one. Another problem I just wanted to show you is, so let us take a very simple neural network. So this is just to show you, like, okay, so what could be the problem actually. So now in this case, I have, like, okay, so the 4 inputs. Okay, I have 4 input. That means r to the power of 4. So I have 4 dimension features. I have extracted 4 dimension features, and I have one hidden layer with 4 neurons, and one output layer with the activation function. Now, if it is a fully connected network, so the number of connections between the input and the hidden layer is, so 4 cross 4. So you will have a 4 by 4 matrix here, and you will have, like, okay, so 1 cross 4 matrix here, vector, and then finally activation function. And this is the number of this is the kind of operation you will try to perform. I think if you are already familiar with the neural network, I think you know, like, so what kind of function it is being done. Even if you are not familiar with the neural network, you need not to worry about, like, we just try to see, like, so the number of computations here. Okay, so in this case, the number of computations being performed in this particular very simple network, where I have 4 inputs and one hidden layer with 4 neurons, and only one neuron output layer. So the number of operations being done is, or the your size of your the parameters is this much actually: 4 into 4, 16 plus 4 plus 1. This is the number of trainable parameters, okay, which decides the size of the model. So very important concept, and very important thing to be remembered here is, so your model size depends on this. Now the question is, let us take, like, so let us go back to our original problem of given an image to classify whether image is a indoor image or outdoor image. So let us say my image is still a low resolution image. So it has got only 400 cross 400. That means 400 pixel by 400 pixel. Today we are talking about 100 megapixel image, or like, so the image taken with 100 megapixel camera, or like, so 18 megapixel, 20 megapixel camera. Okay, so even for a simple case of this particular image, where I have a 400 pixel into 400 pixel and 3 channels, RGB channels. So now, if I try to flatten this, if I try to take each and every pixel as an input for this, just for the study, so the number of inputs turns out to be, like, so 480,000, 480,000 inputs. And again, if I construct only one hidden layer with same number of neurons as that of the input, that means 480,000 or the 480,000 neurons in one hidden layer. Okay, my network is not a deep network now. My network is still a shallow network, and not even a fat network. Okay, it has got only one input layer is 480,000 neurons inputs and 480,000 neurons in one hidden layer. The number of trainable parameters will be about 230 billion. Getting the problem. So even a very, very simple toy problem with these kind of cases, right? It becomes extremely difficult to train this kind of models. Right? Even if you reduce the number of neurons here by 1,000 instead of 480,000, so the number of trainable parameters turns out to be about 480 million. Getting the problem. So this is where so the traditional neural networks, right? So even though so the initially neural network was first neural network was developed in 1970s. So why neural network didn't become popular until recently because of these kind of problems, like exponential growth, exponential expansion in the number of data points that need to be processed. However, so with the recent development model, so the handling this kind of data is not a problem, but we are talking about a type problem. So however, so if we take a very, very sophisticated problem, so I want to find some kind of patterns in satellite images. Well, this is extremely difficult because the kind of resolution you get it in that kind of satellite images are extremely large. How are you going to handle this? Okay, so that's where so the problem becomes exponential, so the problem, right? So this is where the traditional AI, so even with the help of our the CNNs and with sophisticated GPUs, everything, but amount of problems you can solve and the kind of data you can handle is always a problem. There is a limitation. So we need to have a alternative way of looking this problem or solving this problem, and this is where probably the quantum computing can definitely help or so bring in so radically different way of solving the problems and produce a much more effective results with a fraction of computing power, right? So I'll just quickly run through the applications of AI. I think probably we don't have much time. So one of the very, very interesting problem, so today we are seeing so the huge amount of opportunities industry automation. So at Samsung we work on so the automating the manufacturing process at various stages. Okay, so starting from inspection to recipe prediction to okay, so the optimization of the parameters and the downtime prediction, anomaly detection, and time to failure of the machines, and scheduling the manufacturing process, everything. So there are a whole lot of problems so the manufacturing industry is trying to solve, and I'm sure so the amount of jobs being created by AI in the area of industry automation is going to grow significantly for next at least for next 5 to 7 years because many industries every industries want to embrace AI technology and they want to solve the problem of automation. They want to automate their manufacturing process. They want to increase their productivity. They want to minimize their outflows or so the defects. Okay, so this is one area so where uh, if you are practicing AI even with the help of a traditional computing, right? So huge amount of opportunity, and so because of the limitation and the challenges of the amount of infrastructure required to solve this kind of problem, right? Even if you come up with a quantum algorithms which can optimize and generate this kind of solve the problem with even in the simulation mode, right? So it is extremely useful, and there will be a lot of opportunities it can throw over. Okay, both for classical as well as the quantum AI applications. And again so the speech understanding and voice assistance. So today we are so the chat GPT and so these are getting integrated with the voice, and we are talking about the language LLMs. So where so it can interpret, interact, and it generate the result using the multiple languages, multiple conversations. So there is a very, very interesting problems can be solved. And again, AI and is at the cornerstone. And of course, like a lot of problems can be solved with the help of quantum computing, mainly from the point of optimization of these kind of algorithms by fine tuning these algorithms. Right. And of course, like, so the biometrics. So the crypto, the encryption. So quantum computing has already proven that, okay, so it can give like, so utmost level of encryption compared to your traditional models. And whenever there is a involvement in the biometrics, right? So securing these biometric IDs, okay. So with the help of quantum computing could be very, very interesting application one can always think of. Okay, so trend prediction, recommendation systems. So of course, like, so the current classical models are also performing extremely good, and they are recommending. But so the assessment of recommendation system is always like, so with respect to the outcome. So that means I can recommend hundreds of things, but whether that recommendation results in buying it, or like, so the converting it into a business deal is very, very important. And this is where, like, so the quantum computing can really, quantum algorithms can really bring in, like, so the quite interesting algorithms, like, so not only recommending, so recommending and ensuring, like, so you are recommending only those items, so which results in the business transactions. So that's also very, very interesting application one can think of. And summarizations. So this is where, like, so how concisely I can summarize the data, yet it is meaningful. This is one more very interesting use case which can effectively be solved using the quantum computing. Now the question is, how are we going to modify the algorithm? I think this is where, like, so we need to put into the practice, like, so what kind of just a minute. So where, like, so we can what kind of algorithm or what kind of modification has to be done to bring the traditional algorithms or alternative algorithms to work in the quantum framework. Yeah, this is effective marketing. I will just quickly yes. And conversational AIs, like, so the GPT models are the chatbots. So again, there is a lot of scope for embeddings, to learn the embeddings, effective embeddings using the quantum algorithms. So mainly from the point of generating a very effective embeddings, and also from the optimization standpoint. Okay. Yeah. So with that application, let me summarize, like, so the challenges in traditional AI. So one of the main challenge in the traditional AI is training complex models. Okay. So even with the sophisticated AI, GPUs and etc. and so forth, so having a supporting the complex models is still a bottleneck, and soon we may enter into a stage where, like, so this some of the problems could be like, okay, so cannot be solved with the help of the traditional classical AI framework, or the classical computing model actually. So in spite of, like, so today we are talking about, like, so the very, very optimized models, like, so we are trying to talk about, like, so the small language models, etc. and so forth. So there is optimization is happening from the traditional computing model, but not only, like, so the complex models. So complex model mainly from the point of the data complexity standpoint. Okay, when your data is very, very complex, and, like, so it has got a very dynamic ranges in the data aspect, how do we bring those kind of models in a small language models, or the small machine learning models, is extremely difficult. Definitely, like, so this is where we need to leverage a quantum computing. And again, data intensive tasks is going to be severely impacted. Either it takes too much of time to generate the response, or there is a significant limitation in the amount of data being generated. Even today, we are talking about the RAG models, or the language models. The number of tokens being generated, if you can generate, like, more number of tokens, so your output could be more effective and meaningful. But because of the computation limitation, right, So the amount of tokens being generated is very limited, and because of that, the quality of the output could also be very, very limited actually. And there is, because of all this, we are using high-end GPUs, right? So they are consuming a lot of powers, and there is a huge requirement for the cooling. Okay, so these kind of things can be effectively solved using the quantum computing, because quantum models are expected to like consume fractional of power compared to the traditional computing models. Okay, so that way, like, so they are highly optimized for a specific task. So that way, like, so these things can be effectively overcome with the help of quantum models and data storage and security of the data. So today, one of the problems like so we are envisaging is so we are using a lot of data to train the model. What happens if the data itself is somebody tampers this data itself? Okay, then the output or the outcome of your machine learning models cannot be reliable. Okay, and you won't be able to repeat the experiments. So this is where like so the quantum computers can help to secure this data, training data sets in the machine learning. This is another area where like so the quantum AI or the quantum computing can bridge the gap for the AI. Okay, so these are the some of the challenges. Of course, these are not exhaustive in nature. So I come up with some of the top challenges, like so which many researchers are trying to address from the point of like so the quantum computing, mainly like so how the quantum computing can bridge the traditional AI. And these are the bridging gap with quantum AI. So we have a quantum parallelization, as we discussed earlier, right? So these quantum models are like highly parallel in nature. So because of this, like so some of the complex calculation and multiple calculation can be achieved with the help of a very powerful concept called superposition. So I'm not getting into the details of this one. Probably like okay, so in my next session, when I talk about the quantum circuits, I will talk about how to build this kind of superposition, entanglement, and qubit. So I think probably you already aware of these kind of things. So that's the reason I'm not getting into this one. But with the help of superposition, so this quantum parallelization, we can achieve multiple calculation, and exponential speed up is possible to train the complex models and complex data sets. So as already proven, so these quantum computers are expected to consume less energy because they are highly efficient and optimized for, compared to their classical counterparts. Quantum memory, so this can process the data at quantum states. So because of the data teleportation, right? So you can process the data in quantum states. Because of that, like so the amount of memory bits it can handle at any point of time. So it could be like so extremely large, and because of this, so you can have a larger batch size when you're training your data sets or the ML models. So currently, like so, the batch size are restricted by the type of GPUs you are using, right? So this can significantly overcome with the help of quantum computing. With you can have a larger, relatively larger batch size when you are trying to train your quantum models and faster calculations, so which are very very suitable for LLMs and Gen AI. And advantage of AI safety, right? So we are like so you can have a better AI alignment and verification. So it's possible with the help of quantum techniques. Okay. And one of the major limitation of today's machine learning algorithms are the bias and fairness actually. So mostly like so the machine learning algorithms are biased towards that kind of data it is being given. So always like so the bias is one of the killer in the quality of the ML result acceptance. But so the bias and fairness is at the core of the quantum computing. So because of this, I think probably the machine learning algorithms are like so the bias and fairness boundary or the barrier can be effectively crushed with the help of the quantum computer. And quantum computing has got a better error correction. I think previous speaker was also talking about the error correction model, right? So with the quantum error correction, we can have a better training models and the error correction for the weights. so which can shorten your the training period. So currently, like so, the convergence takes longer time because of your error propagation model. With the quantum error corrections, I think probably like so we can significantly reduce the number of training cycles, and error updation could be very effective. Okay. Of course, the major challenge at the same time, the enormous opportunity is in the area of quantum algorithm development itself. Okay, either you can take up a problem and start developing the algorithm from the scratch to fit into a quantum framework, or so take an algorithm which is already very well established in the classical computing framework, and take those algorithms and transform it into a quantum algorithm to work in a quantum framework. So this itself could be like so a significant opportunity for you to explore. Okay, so it has got a lot of potential and a lot of opportunities where so you need not to worry about like so the quantum computing aspect. If you're an algorithm engineer, so even to translate these algorithms into quantum framework itself is a good opportunity, and there are a lot of opportunity one can foresee. Yeah. Yeah, I think with the with limited time, I just rushed through the some of the concept. I think how uh, what aspects of AI problem like so which can be effectively solved with the help of quantum AI. I think probably with some references, I will share the references where like so you can get more detail about like so the how to address the bias and fairness with the quantum framework, etc. and so forth. I think probably from that point you can start reading, and then you can start working towards that. I think definitely it will create a lot of career opportunity, both from the point of quantum computing. Of course, like so, one of the powerful combination, if we are talking about today, is the technology where like so the AI is already established and powerful technology, and quantum computing where we are seeing like so the lot of computing advantage it can bring in, and clubbing these two technologies definitely will have like so a super edge in creating a very niche career areas, as well as like so some of the very interesting problems can be solved. Yeah. With that, so if you have any questions, you can ask me so that we can discuss maybe one or two questions, and then can call for the day. Any questions? So I think there are a few questions posted in the chat. So with error detection and correction, right? So basically, like okay, so if you are looking into like okay, so the error correction models with respect to the quantum error, so there are already like so there are a lot of algorithms with quantum error detection and correction methods with respect to the quantum mechanism that you can always start and you try to understand, and mainly from the point of the machine learning or the AI, if you're talking about, so try to understand like so the different propagation, back propagation, and different type of loss functions what we are having, and how to translate those the loss functions into a quantum loss states, right? So that could be like so your starting point actually. Like for example, if I am talking about the classical classification problem where I'm trying to use a cross entropy loss. How to translate this cross entropy loss into like so the quantum framework could be your starting point, and from that point you start and start transforming your framework, your entire algorithm into the framework of the quantum algorithm. Okay, and from the quantum algorithm itself, there are like a lot of algorithms already being discussed, and like so people are like so researching from the point of error detection and correction. You can start using and leveraging these two things to come up with the effective loss functions which are suitable for the machine learning applications.
There is one another question posted, Dinesh. Can we use quantum machine learning algorithm in a classical computer?
Using a classical, the quantum algorithms and a classical computer may not give like us a lot of advantages actually, right? So why we are taking these classical algorithms to quantum algorithm framework is to get the advantage of like so some of the quantum computing advantage like entanglement and like so the teleportation. So these are the kind of things we are trying to exploit. Okay, so that's the reason we are trying to move from the classical framework to however like so with the current limitation, right, with the limitation in the hardware, like so we don't have a widely available quantum computers available. So there are simulation models, quantum simulation frameworks are built which effectively running on a traditional computers. So using those simulation frameworks, right, quantum simulation frameworks, we can run those algorithms, okay, just to uh, get some numbers and like okay, so the to benchmark so where it stands with respect to the traditional algorithms. But down the line, like so definitely like so there a lot of effort is being put in to make these quantum computers as a reality in a very near future. I think probably once those kind of frameworks are available, we can start porting and start applying to solve the real time problems. Hope I answered this actually. Like so, otherwise, quantum ML algorithms running on a classical computers may not be very. You may not get the similar kind of gain. Of course, like okay, so. The one benefit what you can get is like so with respect to the loss and your the fairness bias paradigm, those can be addressed. Those can be resolved with the help of QML algorithm. But if at all you want to get a full potential out of this, both from the result, the quality of the result, as well as from the computation standpoint, I think probably we need to still wait for some time. But however, like so, with you can start experimenting with respect to this the simulation frameworks. So, any other questions? If you have any other questions, you can just post. If not, you can always send out a questions to my mail ID. I already shared it in the beginning, or you can get it from Madam. So my mail ID is this. I'll just try to. So you can post to this ID. So I'm happy to share more details and also the reference links for some of the materials and some of the algorithms, mainly from the point of QML. Right. So if no further questions, so thank you all for your patience listening, and I hope so it has given some insight about like so what kind of problems like so currently we are trying to solve using classical computer in the area of machine learning. What are the different type of applications? What kind of opportunities is creating? And what are, at the same time, I try to highlight like some of the challenges and the limitations and where we are heading, and then how possibly these limitations, mainly from the QML or the quantum AI, so which can be effectively bridged with the help of quantum computing. So that I just highlighted. Yeah. If it has motivated you to solve some of the problems, I consider myself, my job is accomplished.
Thank you so much, sir. In spite of a very short notice, actually, your session was the first session tomorrow, and then Arun sir's session. Means you were supposed to take the bridging between AI and classical computer, and then
Right.
inclusive of quantum, and then he was supposed to give the reinforcement learning, but due to that schedule change, it became the reverse. Anyway, we had a wonderful session. We were very clearly explaining about the difference between the machine learning and deep learning, and how the quantum can be embedded into that deep learning so that it can reduce the computational complexity. That's what we understood from this. And thank you so much, sir. Thank you for being with us and giving this wonderful session. And I request the participants, like if you have any more questions, please try to post your questions in the sir's mail, as he mentioned in the chat. Thank you.
Thank you, madam. Again, I take this opportunity to thank the organizers for giving me the opportunity to share my views and experience. Yeah, it is. I think questions are also very impressive. I think so there are like so these kind of questions will try to open up like also some kind of forum where we can collaborate and discuss. I think yeah, that's good.
Yes, definitely, sir. Definitely. Maybe it's a very short time constraint as you started a little bit late and it's about more than 9:10. Yeah. So thank you so much, sir, and we will let us wind the session. Thank you for
Thank you, madam.
thank you
Thank you
for
very much.
being here